Here is something worth thinking about as you settle in tonight. Right now, at this very second, while you are listening to these words, something invisible is happening all around you. Through the walls of your room, through your ceiling, through your own body, thousands of radio signals are passing. They are coming from above, from about 22,000 miles up, where bus-sized machines float in total darkness and absolute vacuum. Their enormous solar panel wings turned toward the sun and their antennas aimed down at Earth, beaming narrow rays of invisible microwave radiation toward the surface below. Those rays carry television channels, phone conversations, internet traffic, weather data, navigation signals, billions of bits of information every single second. And every one of those signals traveled a path that, when you stop to think about it, seems almost impossible. Here is why. When a radio signal leaves a ground station antenna and heads up toward a satellite in geostationary orbit, it crosses a distance of roughly 22,000 miles. Along the way, it loses, and this number is real, approximately 99.9999999999999% of its power. It weakens by a factor of 100 billion billion. If you send 1 watt of power upward, the signal that arrives at the satellite carries about 100 billion billionth of a watt. A number so small that to write it out in ordinary decimal form, you would need to put a 0, then a decimal point, then 19 zeros, and only after all of those would the first meaningful digit appear. And after that, the satellite has to amplify this almost nothing and send it back down to Earth, where the signal will lose just as much all over again. And at the end of that journey, from this whisper that has dissolved twice into the void, your television somehow assembles a high-definition picture. Your satellite phone somehow recovers a human voice. It works, reliably, every day, every second, for more than half a century. How? Think about the last time you watched satellite TV during a thunderstorm, and the picture broke apart into little squares. That was rain weakening the signal by maybe 5 or 6 decibels, a factor of 3 or 4. And even that tiny disruption was enough to ruin the image. Now consider that the empty space between the ground and the satellite weakens the signal by 200 decibels, a factor of 100 billion billion. How does anything survive that? What kind of engineering makes it possible to send a human voice 22,000 miles straight up into vacuum to a piece of metal hurtling along its orbit at nearly 7,000 miles an hour, and get that voice back, clear, intelligible, good enough for a conversation? And here is the other thing. If you have ever made a call through a satellite phone, you know there is a strange pause in the conversation, about half a second of silence between your sentence and your listener's response. That pause is not a glitch. It is not the equipment being slow. It is the speed of light itself, the fastest thing in the universe, needing a quarter of a second just to travel from you to the satellite and back. And that quarter of a second is the reason people spent billions of dollars and launched thousands of satellites into orbit, trying to get rid of it. Tonight, we are going to trace the entire journey. We will start at the very beginning, the moment an electrical signal leaves a modem inside a ground station. We will follow it step by step, through cables, through amplifiers, through a parabolic antenna, through rain and atmosphere, across 22,000 miles of cosmic emptiness, all the way to the satellite. We will see what happens inside that satellite, and then we will follow the signal's return path, back down to a receiving antenna, through a low-noise amplifier, back into a modem, and finally into a picture on a screen or a voice in a speaker. We will move slowly because there is no rush. Every stage of this journey is its own story, its own engineering battle, its own quiet victory over physics. And I think that by the end, you will look at the satellite dish on your neighbor's roof a little differently. Because behind that ordinary-looking white circle sits one of the most elegant engineering solutions ever devised. Let us begin. To understand satellite communications, you need to start with the simplest question. What exactly are we sending into space? The answer sounds plain. We are sending a radio wave, an electromagnetic oscillation, the very same phenomenon that carries a signal from an FM radio station to the receiver in your car, or from a Wi-Fi router to your laptop, or from a cell tower to your phone. In every one of these cases, information, voice, video, data, is turned into an electromagnetic wave that travels through space at the speed of light, 186,000 miles per second. And in satellite communications, the exact same thing happens. The principle is identical to any other form of radio communication. The only difference is the distance, and the fact that at the other end of the line, instead of a cell tower on a hill 6 miles away, there is a machine floating in vacuum at an altitude more than 5 times the diameter of the Earth. But let us start on the ground, at the ground station, at the place where the signal is born. Picture a building, or a shipping container, or even a portable suitcase. Yes, those exist. Inside there is equipment, a modulator or modem. This device takes your information, say a television picture, or a stream of computer data, or a digitized human voice, and converts it into a radio signal. The modulator encodes information into an electromagnetic oscillation of a specific shape, a specific frequency, with a specific pattern of changes that carry the encoded message. In simple terms, the modulator takes a sequence of ones and zeros, digital data, and translates it into the language that radio waves speak. But here is what is interesting. The modulator does not create the signal at the frequency it will actually use to reach the satellite. It works in what is called the L band, frequencies of roughly 1 to 2 gigahertz. That is relatively low by satellite standards. Why? Because L band is something like the universal language of indoor equipment. Modems, modulators, demodulators, they all work at these frequencies. Regardless of what frequency will be used to transmit to the satellite, 4 gigahertz, 14, 30, inside the ground station, the signal is always formed at L band first. This is convenient because it means the same indoor equipment can be used with different satellite frequency bands. You do not need a separate modem for every frequency. You use the same modem, and the translation to the actual satellite frequency happens later, in a different device. We will get to it shortly. So the signal is created. It exists as an electrical oscillation at about 1.5 gigahertz, running through a cable. This cable is called the IFL, Inter-Facility Link, and it connects the indoor equipment to whatever is mounted outside. The cable is usually coaxial, like the one that runs from a TV antenna to your television, only thicker and higher quality. And the length of this cable matters, because a signal traveling through a cable loses power. The longer the cable, the greater the loss. In a good system, those losses are small, maybe a few decibels. But in satellite communications, as we will soon see, Every decibel is worth its weight in gold. Every loss, even a small one, will echo at the other end of a 22,000-mile journey. The signal reaches the outdoor equipment, and here it meets a device that does two crucial things. First, it translates the signal from L-band up to the frequency that will actually fly to the satellite. Second, it amplifies the signal's power many times over. This device is called a BUC, block-up converter. And to understand what it does and why, we first need to talk about frequencies. Let us spend a moment longer on the ground station, because it comes in many forms, and each tells you something about the versatility of satellite communication. At one end of the scale, there are the teleports, large commercial ground stations with multiple antennas, each 10 to 40 feet across, serving as hubs for satellite operators. A teleport might have a dozen antennas on its grounds, each aimed at a different satellite, each handling a different service. One feeding a television broadcast, another carrying internet traffic, a third relaying phone calls across an ocean. The facility is air-conditioned, redundantly powered with diesel generators and uninterruptible power supplies, staffed around the clock, and connected to terrestrial fiber optic networks. These are the nerve centers of satellite communication, the places where data enters and leaves the sky. At the other end, there is a traveler with a satellite phone the size of a large mobile handset. The phone has a tiny built-in antenna. Not parabolic, just a stubby stub or a small flat array. It transmits with a fraction of a watt, and yet it connects to a low-orbit satellite passing overhead, which relays the call to a gateway station on the ground, which patches it into the telephone network. The entire architecture of a global satellite system compressed into something that fits in a jacket pocket. Between these extremes, the VSATs, very small aperture terminals, the workhorses of satellite internet and data networks. A VSAT is typically a 2 to 4 foot dish with an integrated BUC and LNB connected to a modem the size of a paperback book. Hundreds of thousands of these are deployed worldwide, on gas stations, bank branches, retail stores, remote clinics, military outposts. Each one maintains a permanent satellite link, typically in Ku or Ka band, providing internet, voice, and data services. And the maritime VSATs, stabilized antennas under radomes, mounted on ship superstructures, maintaining broadband internet at sea. 20 years ago, a ship in the middle of the ocean was effectively cut off from the world, except for expensive and low-quality voice calls. Today, a container ship crossing the Pacific has broadband internet. Crew can video call their families. The shipping company can monitor the vessel's systems in real time, and the captain can download updated weather charts and routing information, all through a white dome on the bridge deck, hiding a small dish that never stops tracking a satellite 22,000 miles overhead, compensating for every wave and every swell. But it is worth saying that the IFL cable is more than just a wire. A single cable can carry several functions at once. The L-band signal from the modem to the BUC for transmission, the L-band signal from the LNB to the modem for reception, control commands for a motorized antenna, telemetry from outdoor equipment, temperature, signal level, alarm status, and even electrical power for the BUC and LNB, all through one coaxial cable or several bundled into one harness. The quality of this cable is critically important. A corroded connector, a cracked jacket, moisture seeping in, and the entire system degrades. Engineers who maintain satellite stations spend a surprising amount of time checking cables and connectors, because the most common cause of problems at a ground station is not a failure of expensive equipment, but simple corrosion on an IFL connector. One more component worth mentioning: filters. Between the feed horn and the BUC or LNB sit bandpass filters that pass only the needed frequencies and block everything else. The world is full of radio emissions: terrestrial transmitters, radars, cell towers, Wi-Fi routers, and all of them generate electromagnetic waves that could theoretically sneak into the receive path and cause interference. A filter is the door that lets in only the signal you want and keeps everything else out. This becomes especially important as terrestrial 5G networks expand into frequencies near the C-band used by satellites. But we will come back to that later. Why does satellite communication work on high frequencies at all? Why not just take an ordinary FM radio station, point its antenna at the sky, and transmit at 100 MHz? The answer has to do with antenna physics and the way radio waves behave at different frequencies. And this is one of those moments where slowing down pays off. Because once you understand this, the rest of the picture becomes clear. A radio wave has a frequency and a wavelength. The two are related simply. The higher the frequency, the shorter the wavelength. FM radio operates at about 100 MHz, 100 million oscillations per second. The wavelength at that frequency is roughly 10 feet. Satellite communication operates at 4 to 40 GHz, 4 to 40 billion oscillations per second. The wavelength at those frequencies ranges from a few inches down to fractions of an inch. These are microwaves, the same microwaves that heat your food in a microwave oven, only aimed in a narrow beam at the sky. And here is why frequency matters. Any antenna works better when it is large compared to the wavelength it transmits or receives. If the wavelength is 10 feet, you need an antenna tens of feet across to focus the signal into a narrow directed beam. That is impractical. But if the wavelength is 1 inch, an antenna just 3 feet across is already enormous from the physics point of view. It spans dozens of wavelengths, and such an antenna can produce a very narrow, very focused beam. The narrower the beam, the more energy you concentrate toward the satellite. The louder, if you like, your voice aimed at the sky. This is why satellite communication uses microwave frequencies. At these frequencies, an antenna of reasonable size, 2 to 10 feet across, can form a beam narrow enough to efficiently reach a satellite. In the world of satellite communications, frequencies are divided into bands, each with its own name and character. Think of them as neighborhoods in a city, each with its own personality. First, C-band, roughly 4 to 8 GHz. C-band is the veteran, the first frequencies widely used for satellite communication, starting in the 1960s and 70s. Its great virtue is weather resistance. Rain, snow, clouds, almost none of it affects a C-band signal. Microwaves at these frequencies pass through rain nearly as easily as light passes through glass. That is why C-band is still heavily used in tropical regions, where torrential downpours are a daily reality. But the price is antenna size. The wavelength in C-band is about 2 to 3 inches, which means that to get a sufficiently narrow beam and enough antenna gain, you need a dish 6 feet across at minimum, and often 10 or 16 feet. Not something you mount on a balcony. Next, KU band. 10 to 18 GHz. KU is probably the most familiar band to ordinary people, because it is what most satellite television and consumer internet access runs on. The wavelength here is about 1 inch. That means the antenna can be noticeably smaller, 3 to 5 feet, and sometimes just 2 feet. that little dish you see on rooftops and balconies. Ku-band sparked a revolution in satellite television, precisely because it made the antenna compact enough for anyone to install at home. But there is a downside. Ku-band is more sensitive to rain. A heavy downpour can weaken the signal enough to make the TV picture break into blocks or disappear entirely. If you have ever watched satellite TV stutter during a thunderstorm, that is rain hitting the Ku-band signal. There is also X-band, 8 to 12 GHz. It is used mainly by the military, which values its good compromise between antenna size and rain resistance, and its suitability for communication on the move, from ships, aircraft, military vehicles. And finally, Ka-band, 26 to 40 GHz. These are the highest frequencies currently in active commercial use for satellite communication. The wavelength here is less than half an inch. Antennas can be very small, 2 feet or even smaller. Ka-band is the future of broadband satellite internet. But in Ka-band, rain is a real enemy. Water droplets at these frequencies absorb microwaves very efficiently. Heavy rain can cause losses of 10, 15, even 20 decibels, meaning the signal is weakened by a factor of 10 to 100 simply because there is a downpour between you and the satellite. Notice the pattern. The higher the frequency, the smaller the antenna, and the more data you can send. But the more vulnerable the signal becomes to rain. The lower the frequency, the more reliable the link in any weather. But the bigger the antenna, and the narrower the bandwidth. Satellite engineers live inside this trade-off every single day. Every project, every system is a choice. What matters more to you? Compactness and speed, or reliability in a storm? Let me add a few more details about each frequency band, because the trade-offs are richer than they first appear. In C-band, the resilience to rain comes with another cost beyond antenna size: interference from terrestrial systems. Because C-band frequencies overlap with terrestrial microwave links and increasingly with 5G cellular networks, satellite Earth stations in C-band must sometimes contend with interference from nearby ground transmitters. This is especially problematic in urban areas where the radio environment is crowded. Many satellite operators have begun migrating services from C-band to Ku or Ka to escape this growing interference. A migration accelerated by regulatory decisions in several countries to auction portions of C-band spectrum to 5G operators. Ku-band's sensitivity to rain has a practical consequence that most viewers of satellite TV have experienced. During a heavy storm, the picture freezes, breaks into colored blocks, and then disappears entirely. This is called rain fade. The technical explanation is that the signal-to-noise ratio has dropped below the threshold needed for the error correction codes to function. Once the rain weakens or stops, the picture snaps back instantly. The system is designed to handle a certain level of rain, the rain margin we discussed. And for most locations, the link works through all but the heaviest storms. In a temperate climate, outages due to rain might total a few hours per year. In a tropical climate, they can be more frequent, which is why tropical broadcasters often prefer C-band despite the larger antenna requirement. Ka-band, for all its rain vulnerability, offers something the other bands cannot: enormous bandwidth. The allocated spectrum in Ka-band is several times wider than in Ku or C. More bandwidth means more data can be transmitted simultaneously. This is why Ka-band is the backbone of modern high-throughput satellite systems. the ones that deliver broadband internet to hundreds of thousands of users from a single satellite. The penalty of rain fade is managed through adaptive coding and modulation. When rain hits, the system automatically switches to a more robust, but slower transmission mode, maintaining the link at reduced speed rather than losing it entirely. When the sky clears, it switches back to full speed. The user may notice a temporary slowdown during a storm, but rarely a complete outage. One more thing about frequency bands. There are proposals and experiments with even higher frequencies, the Q band around 40 GHz and the V band around 60 GHz. At these frequencies, the available bandwidth is enormous, but the atmospheric challenges are severe. Around 60 GHz, there is a strong oxygen absorption line. The atmosphere is essentially opaque at that exact frequency. This makes 60 GHz nearly useless for ground-to-satellite links, but potentially useful for satellite-to-satellite links, where there is no atmosphere to absorb the signal. The atmosphere, once again, both constrains and channels engineering choices. There is one more important detail about frequencies. In satellite communication, the frequency used to transmit from Earth up to the satellite, the uplink, is always higher than the frequency used to transmit from the satellite back down, the downlink. Always, in every band. For example, in Ku band, the uplink is at 14 GHz and the downlink is at 11 to 12. Why? Because free space path loss increases with frequency. The higher the frequency, the greater the loss. And it makes more sense to send the signal on a higher frequency from the ground, where you have access to the power grid, where you can install an amplifier of any power and an antenna of any size, than to force the satellite, which runs on solar panels and has limited power, to transmit on a higher frequency. Let the satellite work on the slightly lower downlink frequency, where the loss is slightly less, and save every watt. Besides, using different frequencies for uplink and downlink solves another problem. If the satellite received and transmitted on the same frequency, its own transmitter would drown out its own receiver. It is like trying to hear a whisper while someone screams in your ear. Frequency separation solves this neatly. The satellite listens on one frequency and speaks on another, and the two signals do not interfere. So, back to our signal. It was born in a modulator at L band, about 1.5 GHz. It traveled by cable to the outdoor equipment, and now it needs to jump to the working satellite frequency, say 14 GHz for a Ku band uplink. That is the job of the BUC, the block up converter. The BUC does exactly two things. It translates the signal frequency from L band to the satellite band, and it amplifies the signal power many times over. At the input, a weak signal at 1.5 GHz. At the output, a powerful signal at 14 GHz. The output power of a BUC can range from a few watts for a small portable station up to hundreds of watts or even a kilowatt for a large fixed installation. And this amplified, frequency-shifted signal is fed into the antenna. And here begins what may be the most beautiful part of the story. Because the antenna is not just a piece of metal. The antenna is geometry turned into a weapon. The parabola. You probably remember this curve from school math, the graph of y equals x squared, a simple symmetrical arc. And this curve has one astonishing geometric property that people noticed as far back as antiquity, long before algebra existed. If you take a parabola and rotate it around its axis of symmetry, you get a bowl, a paraboloid. And here is the property. Any ray, arriving parallel to the axis of that bowl, upon reflecting off its surface, hits exactly one point, the focus. Every parallel ray, no matter where on the surface it lands, converges in the same spot. This is true for rays of light, it is true for sound waves, and it is absolutely true for radio waves. This is why satellite antennas have a parabolic shape. They literally collect the scattered energy of incoming radio waves and focus it into a single point, the way a magnifying glass focuses sunlight. At that focal point sits a device called the feed horn. It is, essentially, the antenna's eye. The feed horn gathers all the focused energy and passes it to the receiver. Or, if the antenna is transmitting, the process works in reverse. The feed horn radiates radio waves, they spread in a cone, reflect off the parabolic surface, and after reflection, they become a parallel beam, a narrow directed ray aimed at the satellite. This is symmetry at work. A parabola works equally well for receiving and transmitting. If the antenna focuses an incoming signal well, it focuses an outgoing signal just as well. This fundamental property of all antennas is described by a quantity engineers call antenna gain. Antenna gain is a measure of how effectively the antenna concentrates energy in one direction compared to a hypothetical antenna that radiates equally in all directions. Imagine a bare light bulb. It shines in every direction uniformly. Now imagine a spotlight. It takes the same light and gathers it into a narrow beam. The spotlight does not create more light than the bulb. It simply redirects the light that the bulb was sending everywhere into one direction. The result is a much brighter beam in that direction. That is gain. A parabolic antenna is a radio frequency spotlight. It takes the power radiated by the feed horn and concentrates it into a narrow beam aimed at the satellite. And the larger the antenna compared to the wavelength, the narrower the beam and the greater the gain. Let us feel the scale. A typical ground station antenna for Ku band might be 10 feet across. At 14 gigahertz, where the wavelength is about an inch, that 10-foot antenna spans roughly 150 wavelengths. The gain of such an antenna is on the order of 47 to 50 decibels. 50 decibels means a factor of 100,000. The antenna concentrates the transmitter's power 100,000 times compared to radiating in all directions. If your transmitter puts out 10 watts, then in the direction of the satellite, your antenna creates an effect equivalent to 1,000,000 watts radiated uniformly. 1,000,000 watts from 10. All thanks to the geometry of a parabola. Engineers have a term for this, EIRP, effective isotropic radiated power. It is the product of the transmitter power and the antenna gain. And EIRP is, in essence, how loudly your ground station is shouting at the satellite. Now let us think about the satellite side. The satellite also has an antenna, but the situation is very different. The satellite is limited in size and weight. Launching it to orbit costs, based on recent figures, roughly $60,000 per pound. Every extra ounce is real money. So the satellite's antenna is typically much smaller than the ground station's. Its gain is lower, perhaps 17 to 20 decibels, corresponding to a factor of 50 to 100. Not 100,000 like the ground station, 50. That is a big difference. But the ground station can compensate. It can install a bigger antenna, a more powerful amplifier. On the ground, there are no weight constraints. On the ground, there is a power outlet. And that is exactly why, as we discussed, the uplink is always at a higher frequency and higher power. The ground station can afford it. There are different designs for parabolic antennas, each with its own engineering trade-offs. Cassegrain antennas, named after the 17th century French physicist, use a small secondary hyperbolic mirror in front of the main reflector, redirecting the signal to a feed horn mounted behind the dish rather than in front of it on a long stalk. This is convenient for large professional antennas. Offset antennas, the ones you see on the sides of houses, have the feed horn positioned off to the side so it does not block the reflector surface. The dish appears to look downward, even though the beam is actually aimed upward at the satellite. All of these are different ways of harnessing the same parabolic geometry. The physics is one. The engineering is many. So, our signal, amplified by the BUC, shifted to the working frequency, focused by the parabolic antenna into a narrow directed beam, leaves the antenna and heads upward, toward the satellite, into the sky. But before it reaches the satellite, it must pass through what engineers, with a touch of drama, call free space path loss. And before it gets to free space, the signal must pass through the atmosphere. And the atmosphere is not as harmless a companion as it might seem. Before the signal leaves the antenna and sets off on its journey, a few more words about how the antenna is aimed, because here hides another beautiful detail of satellite engineering that usually stays behind the scenes. A ground station's parabolic antenna must be pointed precisely at the satellite, and precisely here means very precisely. The larger the antenna and the higher the frequency, the narrower its beam and the more exact the aim must be. For a large Ku-band antenna, the beam width can be fractions of a degree. An error of just 1/10 of a degree will cause a noticeable drop in signal level. Half a degree off, and the link may fail entirely. For fixed antennas, working with geostationary satellites, aiming is relatively straightforward. The satellite is stationary, or very nearly so, drifting slightly within its assigned orbital window. The antenna may have an auto-tracking system that makes small corrections. But for portable stations, those flyaway suitcase terminals deployed in field conditions, in disaster zones, at remote events, the aiming must be done by an operator by hand or by an automatic system. The antenna orientation is described by 3 angles. The first is azimuth, the compass direction to the satellite, measured clockwise from north. The second is elevation, the angle between the horizon and the line to the satellite. The third is polarization, the rotation of the feed horn around the antenna axis to match the polarization of the satellite signal. All 3 angles can be calculated from the coordinates of the ground station, latitude and longitude, and the satellite's orbital position, its longitude. Online calculators do this instantly. In the field, the operator uses a compass for azimuth, an inclinometer for elevation, and adjusts polarization by peaking the received signal. Motorized antennas can do all this automatically. They have drives on all 3 axes and a control system that aims by coordinates, then fine-tunes by maximizing the received signal. For shipboard and aircraft antennas, SATCOM on-the-move systems, This is the only option, because the platform is continuously pitching, rolling and yawing, and the antenna must compensate in real time, keeping its narrow beam locked on a point in the sky to within fractions of a degree. Imagine a ship heaving in ocean swells, and the antenna on its deck must hold a beam steady on a spot 22,000 miles away. Gyroscopes, accelerometers, servo motors, all working continuously, countering every roll and every pitch. You have probably seen the white domes on cruise ships or naval vessels, on masts or superstructures. Those domes are radomes, radio-transparent enclosures protecting the antenna and its mechanisms from wind, salt spray, and weather. The radome is made from a material that passes radio waves with minimal loss, usually fiberglass or special polymer composites. It attenuates the signal slightly, maybe half a decibel to a decibel, but protecting the antenna mechanics from the marine environment is well worth it. And there is another issue that arises when either the terminal or the satellite is moving. Doppler shift. When you approach a sound source, the pitch rises. That is the Doppler effect you hear when a siren passes. The same thing happens with radio waves. A low-orbit satellite approaching a ground station at 4 miles per second shifts the signal frequency by tens of kilohertz. The receiver must track and compensate for this shift in real time, or demodulation fails. On geostationary orbit, the effect is almost absent. The satellite is stationary relative to the ground. Almost. Even a geostationary satellite drifts slightly within its orbital window, producing a small, slow Doppler shift. For most applications, it is negligible, but for very narrow bandwidth signals, it is one more factor to account for. Now, back to our signal. It is formed, amplified, focused, and headed upward. In the first few milliseconds, it passes through the troposphere, the lowest 6 to 9 miles of atmosphere, where most of the air, moisture, and weather live. Here it loses anywhere from a fraction of a decibel in clear weather to 20 decibels in the worst Ka band downpour. Within a few tens of milliseconds, it passes through the stratosphere and above. The air is extremely thin, moisture virtually absent, losses minimal. Higher still, the mesosphere, the thermosphere, and finally the ionosphere, where ionized gas can affect radio waves at lower frequencies, but is largely transparent to the microwaves used in satellite communication. About 1/1000th of a second after launch, 1 millisecond, our signal has cleared the entire atmosphere and entered free space. From here to the satellite, pure vacuum. No molecules, no absorption, no scattering. Only distance. Only the inverse square law. Only the relentless weakening proportional to the square of the distance. The signal flies at the speed of light, invisible, inaudible, intangible, and with every mile grows weaker. Not because something is taking its energy, but because that same energy spreads across an ever larger area. After about 120 milliseconds, 1/8 of a second, our signal, having traveled 22,000 miles, reaches the satellite. Once a powerful, focused beam, now a barely detectable disturbance in the electromagnetic field, carrying a power measured in trillionths of a watt. But the satellite's antenna, small as it is, with only 17 to 20 decibels of gain, catches it, and the transponder begins its work. Meanwhile, between satellites, there is only vacuum. No rain, no clouds, no atmospheric absorption. If two satellites want to talk to each other, and in systems like Iridium and Starlink, that is exactly what they do. The only losses are free space path loss over relatively short distances of a few thousand miles, much less than the 22,000-mile path to geostationary orbit. This is why inter-satellite links, both laser and radio frequency, can be very efficient. In the Iridium system, each satellite had 4 radio frequency crosslinks, 2 to neighbors in the same orbital plane and 2 to nearest satellites in adjacent planes. A signal could travel from satellite to satellite, looping around the orbit until it reached a satellite visible from the destination. Your phone in Antarctica could reach a phone in the Arctic without the signal ever touching the ground, except at the 2 endpoints. Starlink inherited and expanded this idea. Its latest generation satellites carry laser inter-satellite links, delivering several gigabits per second per link. Because light in vacuum travels roughly 50% faster than light in glass fiber, light slows down when it enters glass, bending as it refracts. An inter-satellite route through space can theoretically deliver lower latency than an undersea fiber optic cable over the same distance. For certain applications where minimum delay matters, high-frequency trading, online gaming, real-time remote control, a satellite route through vacuum may become preferable to a ground route through glass. The irony. To save milliseconds, we send the signal into space, not because it is shorter, but because light is faster there. Earth's atmosphere is, in the grand scheme, a relatively thin layer of gas. The dense part, the troposphere, extends to a height of roughly 6 to 9 miles. Compared to the 22,000 miles to a geostationary satellite, that is less than 1/2000th of the journey, a trivial fraction. But it is in this thin layer that nearly all the trouble awaiting a radio signal on its way to space is concentrated. Let us start with the most obvious: rain. Water droplets interact with microwaves. Water is a polar molecule, and it absorbs electromagnetic radiation at microwave frequencies very effectively. This is precisely the principle behind the microwave oven. It bathes food in microwaves. The water molecules in the food absorb the energy, and the food heats up. The exact same thing happens when a satellite signal passes through rain. The water droplets absorb part of the signal's energy and scatter another part sideways. The result is that a signal that has passed through rain is weaker than one that passed through clear sky. And here the pattern we already discussed returns. The higher the frequency, the greater the effect of rain. In C-band, at 4 to 6 gigahertz, even a heavy tropical downpour causes losses of only 1 or 2 decibels. Unpleasant but manageable. In Ku band, at 12 to 14 gigahertz, the same downpour can take away 5 to 7 decibels. That is serious. 7 decibels means the signal is weakened by a factor of 5. In Ka band, at 30 gigahertz, rain losses can reach 15 to 20 decibels, a factor of 30 to 100. The signal literally drowns in the rain. But rain is not the only enemy. Snow, hail, clouds, they all contribute. Water vapor in the atmosphere absorbs microwaves, especially at certain frequencies where water molecules have absorption lines. Oxygen contributes too, though less. The ionosphere, the upper layer of the atmosphere, ionized by solar radiation, can introduce phase distortions, though for microwave frequencies, this effect is usually small. And there is one phenomenon that happens twice a year, around the spring and autumn equinoxes: solar outage. Geostationary satellites hang above the equator, and twice a year, the sun's path across the sky passes directly behind the satellite as seen from a ground station. During those moments, they last just a few minutes per day over a few days, The receiving antenna sees the satellite right in front of the sun, and the sun is a tremendously powerful source of radio noise across all frequencies. In that moment, the noise overwhelms the satellite signal and the link can drop. The phenomenon is predictable and brief, and operators prepare for it. But it is another reminder of nature asserting itself. There are also eclipses. Twice a year, around the same equinox seasons, the Earth passes between the Sun and the geostationary satellite. The satellite enters the Earth's shadow. Its solar panels stop generating power. The satellite switches to batteries. At peak, the shadow can cover the satellite for up to about 70 minutes. 70 minutes without sunlight. The batteries must be large enough to keep all systems running throughout. Another design requirement, another line in the endless list of things that could go wrong. There is a curious piece of physics trivia hidden in these atmospheric details. The very same technology, the microwave oven, that causes trouble for satellite communication, water-absorbing microwaves, was discovered, according to one popular account, thanks to radar work. In 1945, the same year Arthur Clarke published his article about geostationary satellites, an engineer at the Raytheon Corporation named Percy Spencer was working with a magnetron, a high-power microwave generator used in radar systems. He noticed that a chocolate bar in his pocket had melted. Spencer realized that the microwaves had heated the water in the chocolate, and within 2 years, Raytheon produced the first commercial microwave oven. So the same physical phenomenon, the absorption of microwaves by water, created both a problem for satellite communication and a convenient kitchen appliance. There is a certain irony in physics working both for us and against us at the same time. And one more atmospheric effect worth mentioning. Beyond rain, there are gases that also absorb microwaves. Water vapor, not rain, but the invisible moisture in the air, absorbs radiation at certain frequencies where water molecules have resonance lines. Oxygen contributes too, though less. These losses exist even in perfectly clear weather, and their magnitude depends on temperature, humidity, and the antenna's elevation angle. The lower the antenna looks toward the horizon, the longer the path the signal travels through the atmosphere, and the greater the losses. This is why satellite communication prefers high elevation angles, 10 degrees and above. Below 5 degrees, atmospheric losses and refraction, the bending of the beam in the atmosphere, can make the link unreliable. The elevation angle affects something else too. When the antenna looks at the horizon rather than straight up, it sees more warm ground at the edges of its beam. Warm ground radiates thermal noise. More noise means a worse signal-to-noise ratio. This is another reason satellite links work best when the satellite is high in the sky, and why geostationary orbit works poorly at very high latitudes, from, say, Finland or northern Canada. The satellite appears very low on the horizon, and both atmospheric losses and noise increase. How do engineers deal with all these losses? They build in margin. In English, it is called rain margin, or more broadly, link margin. The idea is simple. You design the system so that in clear weather, the signal power is significantly more than you need, much more, so that when rain comes and takes some of it away, what remains is still enough for the system to work. This is like budgeting money. You know your income, you know your fixed expenses, and you leave a buffer for unexpected costs. If the buffer is sufficient, you survive the unexpected expense. If not, you are in trouble. In satellite communications, the income is the transmitter power and antenna gains. The fixed expenses are the free space path losses we will discuss shortly. And the unexpected costs are rain, atmospheric absorption, and all the other whims of weather. When an engineer designs a satellite link, they compile what is called a link budget. It is literally a spreadsheet listing every source of power, transmitter, antenna gains, and every source of loss, cables, atmosphere, free space. At the bottom is the final number, how much signal power remains after subtracting all the losses, and whether that is enough for the receiver to work. Everything, absolutely everything in that spreadsheet is measured in decibels. Because in decibels, multiplication becomes addition and division becomes subtraction. And an enormously complex calculation involving numbers spanning 20 orders of magnitude reduces to simple arithmetic. But here is what I want you to hold in your mind as we go further. All the atmospheric losses combined, rain, water vapor, oxygen, everything, amount to anywhere from 1 to maybe 15 or 20 decibels, in the very worst case, of a heavy downpour in Ka band. That is a lot. But compared to what awaits our signal beyond the atmosphere, it is a drop in the ocean. Because free space will take 200 decibels. 200. Think about that number. 200 decibels is 10 to the 20th power, a 1 followed by 20 zeros. 100 billion billion. All the rain, all the atmosphere, all the weather. All of it pales before the simple, relentless, utterly indifferent fact that the satellite is far away. Let us slow down, because what we are about to discuss, free space path loss, is the heart of all satellite communication. The main enemy, the central problem, the fundamental physical fact that determines antenna sizes, transmitter powers, receiver sensitivities, the entire architecture of every satellite system ever built. And to understand it, you do not need complicated math. You need one simple picture. Imagine you are standing in the middle of a vast, dark field holding a light bulb, an ordinary 100-watt bulb. It shines equally in every direction. Now imagine a sphere around you, an invisible bubble. Say the radius of that sphere is 3 feet. All the energy from your bulb, all 100 watts, is distributed over the surface of that sphere. The surface area of a sphere 3 feet across is about 113 square feet. So each square foot receives roughly 1 watt. Now expand the sphere. Make the radius 30 feet. The surface area grows as the square of the radius, so it is 100 times larger, about 11,300 square feet. But the energy is the same, 100 watts. So each square foot now receives not 1 watt, but 1/100th of a watt. 100 times less. Expand the radius another 10 times, to 300 feet. The area grows by another factor of 100. Each square foot receives 1/10,000th of a watt. Another 10 times farther, about 6/10ths of a mile, and each square foot receives 100 millionth of a watt. The energy smears across an ever larger surface, and the density of that energy drops relentlessly, proportional to the square of the distance. Double the distance, lose 4 times the signal. Triple it, 9 times. Increase the distance 10-fold, lose 100-fold. This is the inverse square law. It works for light. It works for sound in open space. And it works for radio waves. And it is absolutely merciless at cosmic distances. Let us calculate. A geostationary satellite sits roughly 22,000 miles from a ground station. If our transmitter radiates a signal and we place a receiver at that distance, the surface area of the sphere across which the energy is spread is immense. roughly 16 quadrillion square feet. All the transmitter's power is distributed across this colossal imaginary bubble, and the receiving antenna, which might have an area of a few dozen square feet, captures a tiny, microscopic fraction. The formula for free space path loss in decibels comes out to roughly 205 decibels at a typical Ku band downlink frequency over a geostationary distance. At C-band, about 200. At Ku band uplink, roughly 207. 200 decibels. Let us try to feel what that number means, because decibels are a logarithmic scale, and our brains are poorly suited to intuiting logarithms. 10 decibels is a loss of 10 times. 20 decibels is 100 times. 30 is 1,000. Every 10 decibels adds another zero. 40, 10,000. 50, 100,000. 60, a million. You can see how fast it grows. 100 decibels is 10 billion. 150 is a quadrillion. And 200 is 10 to the 20th. 100 billion billion. If you send 1 watt of power after 200 decibels of loss, what remains is 10 to the minus 20th of a watt. To write that out in decimal, 0.0000000000000001 watts. 20 digits after the decimal point before the first meaningful figure appears. For comparison, the light of a candle, seen from about 0.6 of a mile away, delivers to your retina a power on the order of 10 to the minus 14th of a watt. The signal arriving from a geostationary satellite is about 1 million times weaker than candlelight seen from half a mile. And here is the question that I think is already forming in your mind. If the signal loses virtually all its power on the way to the satellite, and then loses just as much on the way back down, how is it possible to receive anything at all? How do you reconstruct sound, a picture, data, from this nothing? The answer is that 200 decibels is a number you cannot defeat, but you can work around. You cannot defeat it because no engineering will cancel the inverse square law. Distance is distance. But you can work around it by gathering power and sensitivity in pieces, in increments, from both ends of the link. Let us put all the pieces together. Our transmitter outputs, say, 10 watts. The ground station antenna adds 50 decibels of gain. Total EIRP, 60 decibel watts. That is the equivalent of 1 million watts if we were radiating in every direction. But we are not. We are shooting a narrow beam at one point in the sky. Then, 205 decibels of free space path loss. Subtract. 60 minus 205 equals minus 145 decibel watts. That is the signal power arriving at the satellite. Minus 145 decibel watts is roughly 300 trillionths of a watt. Now the satellite's receiving antenna adds its 20 decibels. Total, minus 125 decibel watts at the satellite receiver input. Still unimaginably small, but it is a number that can be worked with, because a modern receiver can extract a useful signal from that level, provided the noise is low enough. And that is the key word, noise, because what matters is not the signal level itself, but its ratio to the noise. You can hear the faintest whisper if there is absolute silence around you. The problem arises when the whisper is drowned in a hum. And in satellite communications, noise is a constant companion that can never be fully eliminated. Where does noise come from? Several sources. The first and most fundamental is thermal noise. Any object whose temperature is above absolute zero, minus 459 degrees Fahrenheit, radiates electromagnetic energy. This is so-called black body radiation. The same phenomenon, incidentally, that launched quantum mechanics when Max Planck in 1900 tried to explain why heated objects glow the way they do. This thermal noise is everywhere, in the receiver, in the cables, in the antenna itself, and even in space. The cosmic microwave background has a temperature of about 5 degrees above absolute zero. When the satellite points its antenna down at the Earth, it sees not only the signal from the ground station, it sees everything within its antenna's field of view. The warm Earth at roughly 80 degrees Fahrenheit, the surroundings of the ground station, and everything else that radiates thermal noise. This noise adds to the useful signal, and the satellite must separate the signal from the noise. In the reverse direction, when a ground station receives a signal from the satellite, the situation is slightly better. The receiving antenna points upward at the sky, and if its beam is narrow enough, it sees a small patch of sky whose background temperature is only a few tens of degrees above absolute zero. Much quieter than the warm Earth that the satellite looks down upon. This is why, incidentally, satellite receiving antennas are aimed as high above the horizon as possible. The higher the elevation angle, the less warm ground and atmosphere enter the antenna's field of view, and the quieter the background. And here a device appears that could be called the quiet hero of all satellite communication. It is not as dramatic as a huge parabolic antenna. It is small, often fits in your hand. But without it, nothing would work. It is the LNB, Low Noise Block Down Converter. But before we get to the LNB and the return path, let us first look at what happens inside the satellite itself. Before we move to the satellite, let us spend a little more time on how a ground station is organized, because behind the neat abbreviations BUC, LNB, IFL stand decisions that each deserve attention. Engineers divide ground station equipment into two parts: the outdoor unit, or ODU, and the indoor unit, or IDU. The outdoor unit is everything exposed to the elements: the antenna, the feed horn, the BUC, the LNB, filters. The indoor unit is modems, modulators, demodulators, routers, servers, everything in a temperature-controlled room or container. Between them runs the IFL cable, carrying the L-band signal and, often, power for the outdoor devices. Why this split? Because modems and modulators are delicate, sensitive electronics that dislike heat, cold, and humidity. The BUC and LNB, on the other hand, must be as close to the antenna as possible, because every foot of cable at the satellite frequency, 14-30 GHz, eats a noticeable amount of power. So the BUC is mounted right on the antenna, literally bolted to the feed horn. So the signal at the satellite frequency travels the shortest possible cable distance. The long IFL cable carries the signal at L-band, where losses are much lower. Between the feed horn and the BUC and LNB, there is usually another device, the OMT, ortho mode transducer. This is a filter that separates polarizations. Remember, the same frequency can be used twice with different polarizations. The OMT is the element that separates horizontal from vertical, or right circular from left circular. One port of the OMT connects to the receive path, LNB, the other to the transmit path, BUC. This way, The antenna can receive on one polarization and transmit on another through the same feed horn and the same reflector surface. For portable stations, flyaway terminals, all this equipment must fit in 2 or 3 transport cases, assemble in 20 to 30 minutes by 1 or 2 operators, and weigh no more than about 220 to 330 pounds total. The antenna in such systems is typically foldable, 2 to 5 feet in diameter, with a segmented reflector that assembles from several petals. These stations are used by journalists in conflict zones, rescue workers after disasters, military field headquarters. When all terrestrial communications are destroyed, no power, no cell towers, no internet, satellite communication is the only channel left, and a small folding dish in a suitcase becomes a lifeline. Another type is SATCOM on the move, antennas mounted on vehicles, ships and aircraft that maintain the link while the platform moves. In aviation, satellite communication provides in-flight Wi-Fi, that service of internet at 35,000 feet that seemed like science fiction 15 years ago, and is now offered by most airlines on long-haul flights. The antenna on the aircraft fuselage, flat, streamlined, electronically steered, continuously tracks the satellite, compensating for banks, turns, and turbulence. All so that you can check your email at 6 miles up, flying at 550 miles per hour. And a word about satellite television, because for most people, this is the most familiar form of satellite communication. Satellite TV is a classic example of one-way communication. One powerful transmitting station, the broadcast center, sends the signal up to the satellite, and the satellite relays it down over a vast area where millions of small receiving dishes catch it simultaneously. Each dish is the familiar parabolic plate on a rooftop with an LNB at the focal point. The signal from the LNB goes by coaxial cable to a satellite receiver, the set-top box plugged into your television, which demodulates and decodes the channels. The beauty of this model is its scalability. Adding one new viewer costs the satellite and the broadcast center nothing. The new viewer simply installs a dish and receiver and catches the same signal that is already raining down. 5 viewers or 5 million, the satellite does not notice the difference. This is what makes geostationary broadcasting economically unique. The cost per viewer approaches 0 as the audience grows. Try achieving that with a terrestrial cable network, where a separate cable must be run to every house. This economics explains why satellite TV still dominates in remote areas where cable infrastructure is absent, and why geostationary satellites will not be replaced by low-orbit constellations for broadcasting. One transmission across an entire continent is a job for one big satellite on a high orbit, not for thousands of small ones flying low. On October 4th, 1957, the Soviet Union launched a small metal sphere weighing about 183 pounds into orbit around the Earth. They called it Sputnik. It had no useful function in today's sense. It did not carry TV channels, relay phone calls, or deliver internet. All it did was transmit a simple radio signal, a short, repeating beep at 20 and 40 megahertz that any radio amateur on Earth could pick up. Beep, beep, beep. Each beep lasted 0.3 of a second, and people around the world, tuning their receivers to the right frequency, listened to that beep and understood that the world had changed. Above their heads, beyond the atmosphere, in the void, a man-made object was flying for the first time in history. Sputnik lasted about 3 months in orbit before burning up in the atmosphere. But it proved one fundamental thing. You can place an object in orbit and it will work. A radio signal can be sent from space and received on Earth. But true satellite communications were still far off, because Sputnik had one obvious problem. It moved. It flew on a low orbit at an altitude of a few hundred miles, completing one full trip around the Earth in about 90 minutes. That meant it was visible from any given point on the surface for only a few minutes each pass before disappearing over the horizon. You cannot build a communication system around a satellite that appears for a few minutes and then vanishes for an hour and a half. For permanent communications, you need the satellite to always be there, always visible, always available.
And here we need to step back, 12 years before Sputnik, to a 4-page article published in October 1945 in the British magazine Wireless World. The author was a 28-year-old former radar instructor for the Royal Air Force named Arthur Charles Clarke. He would later become one of the most famous science fiction writers in history, the author of 2001, A Space Odyssey, and many other works. But in 1945, he was simply an enthusiastic young man with a solid understanding of physics. Clarke's article was titled Extraterrestrial Relays: Can Rocket Stations Give Worldwide Radio Coverage? In it, Clarke laid out an idea that seems obvious today, but was a genuine insight in 1945. He reasoned as follows. There are Kepler's laws, laws of orbital motion formulated by Johannes Kepler in the early 1600s based on the observations of Tycho Brahe. One of these laws says that a satellite's orbital period, the time it takes to complete one loop around the Earth, depends on the orbital altitude. The higher the orbit, the slower the satellite moves, the longer one revolution takes. At an altitude of about 250 miles, the period is roughly 90 minutes. At 12,000 miles, about 12 hours. And here is the key. There is one specific altitude where the orbital period is exactly 24 hours. Exactly as long as the Earth takes to spin once on its axis. That altitude is 22,236 miles above the equator. Think about what that means. If a satellite is at that altitude and moving in the same direction the Earth rotates, it completes one revolution in exactly 24 hours, at the same speed as the surface beneath it. From the point of view of an observer on the ground, such a satellite is motionless. It hangs at one point in the sky, never moving, never setting below the horizon. It just sits there, like a light fixture bolted to the ceiling. Always visible, always available, around the clock, year-round. Clarke realized that such an orbit was ideal for a communications relay. And he went further. He calculated that 3 such satellites, spaced evenly above the equator at 120 degrees of longitude apart, would see virtually the entire surface of the Earth, except for small areas near the poles. 3 satellites, and the whole world is covered. The article was received politely but without excitement. In 1945, rocket technology could not yet lift anything useful to such a height. Clarke later joked that it was perhaps the most profitable invention in history, on which he earned not a penny. He never patented the idea, considering it an obvious consequence of physics. Between Sputnik and the realization of Clarke's vision came several milestones. In December 1958, the American SCORE satellite became the first to transmit a human voice from space. A Christmas greeting from President Eisenhower. In 1960, NASA launched ECHO, a 100-foot diameter aluminum-coated balloon
that passively reflected radio signals from one ground station to another. And in July 1962, Telstar became the first active communications satellite, the first to receive, amplify, and retransmit. Telstar weighed about 170 pounds and orbited too low for continuous service, available for transatlantic links only about 20 minutes per pass. But during those 20 minutes, on July 10, 1962, 200 million viewers in 16 countries saw the first live transatlantic television broadcast. The Statue of Liberty, a baseball game, the Eiffel Tower, all in real time. The age of satellite communication had begun.
Then, on April 6, 1965, Earlybird, officially Intelsat-1, was launched, the first commercial geostationary communications satellite. It weighed about 86 pounds and could support 240 simultaneous phone calls or one television broadcast, not both, either voice or TV. By today's standards, trivial capacity. A home Wi-Fi router handles thousands of times more data per second, but it proved that Clark's idea, outlined in a 4-page article 20 years earlier, worked. The satellite really did hang in one spot. Communication through it really was continuous. And from April 1965 onward, the era of commercial satellite communications was underway. Now let us return to our signal, which has just arrived at the satellite. What happens inside? A communications satellite is, at its core, an extremely expensive, extremely complex, extremely lonely repeater.
Its main job is to receive a signal from a ground station, amplify it, and send it back to Earth. The key word is repeater. In most traditional systems, the satellite does not process the information. It does not decode voice. It does not decompress video. It does not even know what it is carrying. It simply takes the radio signal it received, amplifies it, and sends it back down. Like a mirror that reflects light, except this mirror also amplifies. Inside the satellite, the component that handles this is the transponder. A transponder is essentially one relay channel, a receiver, a frequency converter, an amplifier, and a transmitter. A satellite can carry dozens of transponders, each operating in its own frequency band, each handling a certain slice of spectrum, say 36 MHz wide. Within that slice fits a certain number of phone channels, or 1 or 2 TV channels, or a certain stream of internet data. When the signal arrives from the ground station, the satellite antenna receives it. The signal passes through a low-noise amplifier. Yes, the satellite has its own LNA because the signal arriving from below is unimaginably weak and must be amplified before anything else can be done with it. Then the signal passes through a frequency converter. The uplink frequency is shifted down to the downlink frequency. If the signal arrived at 14 GHz, it is converted to, say, 11 or 12 GHz. This is done for the same reason uplink and downlink use different frequencies, so the satellite's powerful transmitter does not drown out its own receiver. After frequency conversion, the signal enters the power amplifier. Here you find specialized devices, TWTAs, traveling wave tube amplifiers, or SSPAs, solid-state power amplifiers. The output power of a transponder ranges from a few watts to a few dozen watts. That might seem modest for a transmitter, but remember, every watt on a satellite is precious. The satellite runs on solar panels. A typical modern geostationary satellite generates 5 to 20 kilowatts from its solar arrays, and that power must feed not one transponder, but dozens, plus all the systems needed to keep the satellite alive: thermal control, attitude stabilization, orbit correction, telemetry. Most traditional geostationary satellites work as so-called transparent repeaters or bent pipe transponders. The signal is received, frequency shifted, and amplified, but not processed at the data level. The satellite does not decode information, does not route packets, does not analyze content. It simply takes what it received on the uplink and sends it on the downlink, at a different frequency and power level, but with the same content. This makes the satellite simple and reliable. The less processing, the less that can break. But there is another approach: regenerative satellites, or satellites with onboard processing. Such a satellite actually decodes the incoming signal, processes the data, can switch it between different antenna beams, route it between transponders, and re-encodes it for downlink transmission. This is significantly more complex, but offers an important advantage: the ability to fix the signal on board. If the uplink had bad weather and the signal arrived with errors, a regenerative satellite can correct those errors before retransmitting, instead of blindly relaying a damaged signal. This matters greatly for high-throughput systems and satellites serving many ground stations simultaneously. Modern high-throughput satellites increasingly use onboard processing, if not full regeneration, then flexible routing of signals between dozens or hundreds of beams. The satellite transforms from a passive mirror into an active network node hanging in space. But the more complex the onboard electronics, the higher the risk of failure, and the more critical the need for redundancy and careful design. And the heavier and more expensive the spacecraft, and the more costly the launch. Everything loops back to trade-offs. A simple, transparent repeater. Reliable, light, cheap, but inflexible. A regenerative satellite with onboard processing. Flexible and efficient, but complex, heavy, and expensive. The engineer chooses based on the mission. And a word about security. A transparent repeater provides no information protection whatsoever. It relays everything it receives without discrimination. Anyone who points an antenna of the right size at the right satellite and tunes to the right frequency can receive the signal. For television broadcasting, this is fine. The signal is meant for everyone. But for commercial data, military communications, banking transactions, an obvious problem. The solution is encryption on the ground. Data is encrypted before it reaches the modulator and decrypted after the demodulator. The satellite carries an encrypted stream whose content it does not know, and intercepting that stream is useless without the decryption key. Security is the ground equipment's responsibility, not the satellite's. And here we arrive at what makes a satellite a truly unique machine. A satellite cannot be repaired. After launch, that is it. No one will come to replace a burned-out transponder. No one will tighten a loose bolt. No one will upgrade an aging amplifier. The satellite must operate autonomously, without any physical maintenance, for 15 to 20 years. Think about what that means for the engineer designing it. Every component must be rated for vacuum, for temperature swings from about 300 degrees Fahrenheit on the sun-facing side to minus 250 on the shadow side, for constant bombardment by micrometeorites and cosmic radiation. There must be backup systems, redundant transponders, redundant amplifiers, redundant control elements. Because when something fails, and in 15 years, something will fail, the only repair option is switching to a spare remotely from Earth. Physical repair is out of the question. The launch itself is a moment of tremendous tension. A modern geostationary satellite costs $200 to $400 million, including launch. It is designed over 3 to 5 years. Assembled in a clean room. every component tested dozens of times. And then it rides atop a rocket, subjected to forces of 4 to 5 G, vibrations, and acoustic pressure of about 160 decibels for 6 minutes. Everything that engineers built over years endures a 6-minute stress test. If it survives, it works. For 15 years, without a break. When the satellite's orbit correction fuel runs out at the end of its life, it is commanded to fire its thrusters one last time, raising itself about 200 miles above the working orbit to a disposal orbit, the graveyard orbit. There it will drift for centuries, dead and silent, its solar panels still catching sunlight but with no one to transmit to. A quiet monument to engineering, hanging in the void. The launch itself deserves a few more words, because it is perhaps the most nerve-wracking moment in any satellite project. A modern geostationary communications satellite costs $200 to $400 million, including launch. It is designed over 3 to 5 years. Assembled in a clean room, a sealed facility with filtered air, where engineers wear protective suits so that not a single speck of dust lands on the optics or electronics. Every component is tested dozens of times. The satellite undergoes vibration testing, simulating the G-forces of launch. Thermal vacuum testing, simulating work in vacuum and extreme temperatures. Electromagnetic compatibility testing, verifying that all systems work together without interference. Only after passing all tests is the satellite packed into a special container and transported, often by cargo aircraft, to the launch site. And then it is on the launch pad, mounted under the rocket's fairing. Countdown. Ignition. The rocket rises. For 6 minutes, the satellite endures 4 to 5 Gs of acceleration, vibration, and acoustic pressure of roughly 160 decibels, the equivalent of standing next to a jet engine. Everything the engineers built over years faces a 6-minute trial by fire. About 30 minutes after liftoff, the upper stage delivers the satellite to a transfer orbit, an elliptical path with its low point about 125 miles up and its high point at about 22,000 miles. The satellite separates from the rocket, deploys its solar panels, fires its own engine, and over days or weeks, through a series of burns at the high point, raises its low point and circularizes the orbit at 22,000 miles. When the satellite reaches its assigned orbital position, the commissioning period begins. In-orbit testing. Every system is checked remotely from the ground. Every transponder is tested. Every antenna is calibrated. Every beam is verified against design parameters. This takes several weeks. Only after completion is the satellite handed over to the operator and begins commercial service. From that moment until the end of its life, 15, 20 years, the satellite will work continuously, day and night, without weekends or holidays. The only interruptions are brief eclipses twice a year and occasional orbit correction maneuvers. The rest of the time, continuous relay, thousands of channels, millions of conversations, billions of bits of data, every second. And when, after 15 or 20 years, the fuel for orbit correction runs low, the operator sends the satellite its final command. The thrusters fire one last time, raising the satellite about 200 miles above the working orbit to the graveyard orbit. The solar panels are oriented to a safe position, the transmitters are switched off, and the satellite falls silent forever, beginning its eternal, quiet drift in the void. A dead machine on a dead orbit, beside hundreds of other silent predecessors and neighbors. But down below, on the working orbit, its successor has already taken its place. Newer, more powerful, with greater capacity, better solar panels, more sensitive receivers. And the cycle begins again. Design, assembly, testing, launch, commissioning. 15 years of unbroken work. And again, silence. This cyclicality, birth, labor, death, replacement, gives satellite communication a strange, almost organic quality. Satellites are born in clean rooms, live in vacuum, work until exhaustion, and die quietly, yielding to the next generation. Like trees in a forest, like generations of people. Machines that, if you squint, look a little like living things, solitary, patient, carrying out their task without complaint and without reward. But our signal is inside a working satellite. It has passed through the transponder, received, frequency shifted, amplified, and is now being fed to the satellite's transmitting antenna for the journey back down. The signal leaves the satellite antenna and heads back down toward Earth. And along the way, the exact same thing happens as on the way up, only in reverse. First, 22,000 miles of free space. Once again, the inverse square law. Once again, 200 plus decibels of loss. The signal that the satellite amplifier so painstakingly restored and pumped with power dissolves into the void within a fraction of a second, spreading across the surface of an immense imaginary sphere. By the time the radio wave reaches the surface of the Earth, the watts the transponder produced have been reduced to roughly minus 120 to minus 130 decibel watts. Once again, trillionths of a watt. Once again, almost nothing. Then, the atmosphere. Once again, rain, water vapor, the same losses we already discussed. A few decibels in good weather, a dozen or more in heavy rain. The signal passes through all these layers and finally reaches the receiving antenna. And here begins the most delicate, most precise stage of the entire journey. Because the signal that has come from space is unimaginably weak. It is a whisper against the thermal hum of the universe. And the engineer's task is to hear that whisper without adding noise of their own. The parabolic antenna does the first part of the work. It collects the scattered radio wave energy from across its entire surface and focuses it in the feed horn. If the antenna is large, 10, 16, 30 feet across, it intercepts more energy and provides more gain. A typical Ku-band receiving antenna can deliver 50 to 52 decibels of gain. That means the signal at the antenna output is 100,000 to 150,000 times stronger than the signal falling on a patch of ground next to the antenna. The antenna literally pulls energy out of the air, but even after that amplification, the signal is still extremely weak. And here the LNB, the low noise block down converter, takes the stage. A small device, usually mounted right at the feed horn on the antenna's focal support. You have certainly seen it on satellite dishes, a small box at the end of the arm in front of the dish. That is where the magic happens. The LNB does two things. First, it amplifies the signal, but in a special way, with the minimum possible addition of its own noise. Hence, the low noise in the name. The quality of an LNB is measured by its noise temperature. The lower it is, the less noise the amplifier adds to the useful signal. A good Ku-band LNB might have a noise temperature of 40 to 60 kelvins. For Ka-band, somewhat higher, 100 to 200 kelvins. The lower this number, the better, and the more expensive the device. The LNB's second function is frequency conversion. The signal arrives at the satellite frequency, say 11 to 12 gigahertz for Ku-band downlink. The LNB translates it down to L-band, about 1 to 2 gigahertz. The same L-band where the modems and demodulators work. After the LNB, the signal travels back inside the station through the IFL cable, where the demodulator or modem extracts the encoded information. Bits, ones and zeros. Voice, picture, data, When engineers first faced the challenge of transmitting digital data through a satellite, they found a predictable thing: noise corrupts data. Bits transmitted through a noisy channel arrive with errors. Some zeros arrive as ones, and vice versa. With a weak signal, and the satellite signal is by definition weak, the error rate can be significant. 1 bit in 1,000, 1 in 100, depending on conditions. For old-fashioned analog voice, this manifested as noise and static, tolerable. But for digital data, files, video, internet traffic, even one error in 1,000,000 bits can be critical. The answer is forward error correction coding. The idea goes back to Claude Shannon, although the specific codes were developed by others. The concept: before transmission, extra redundant bits are added to the original data, calculated by a mathematical algorithm based on the original data. These extra bits carry no new information. They are a kind of checksum, an insurance policy. On the receiving side, the decoder analyzes the entire received sequence, data and check bits together, and can detect and correct errors without requesting retransmission. This is hugely important for satellite communication. If the receiver had to request retransmission for every error, and that request travels to the satellite and back with a quarter-second delay each way, the effective data rate would collapse to an unacceptable level. Forward error correction allows the vast majority of errors to be fixed on the fly, without retransmission. Behind this lie decades of mathematical research, from Reed-Solomon codes of the 1950s to modern LDPC codes, low-density parity check, and turbo codes, which bring real-world throughput within a fraction of a decibel of Shannon's theoretical limit.
If Shannon was the person who determined how much information can, in principle, be transmitted through a noisy channel, then LDPC and turbo codes are the tools that approach that limit to within touching distance. The gap between Shannon's theoretical maximum and what modern codes achieve is tenths of a decibel. Mathematics has essentially reached the ceiling, and this fact, as we discussed, means that further increases in throughput depend not on smarter coding, but on architectural decisions. More spectrum, more beams, more satellites. And here, at this final stage, another invisible hero goes to work: the mathematics of error correction coding. The signal, having traveled roughly 44,000 miles in total, 22,000 up and the same back down, weakened by 200 decibels twice, battered by rain and atmosphere. This signal contains errors. Some bits have been flipped by noise. Zeros became ones and vice versa. If we simply transmitted raw data, the link quality would be unacceptable. But before transmission, the data is specially encoded. Extra redundant bits are added, computed from the original data using mathematical algorithms. These extra bits carry no new information. They are a kind of checksum, an insurance policy. On the receiving end, the decoder analyzes the entire received sequence, data and check bits together, and can detect and correct errors without requesting retransmission. This is enormously important for satellite communication, because if the receiver had to request retransmission for every error, and that request and response would travel through the satellite with a quarter-second delay each way, the effective data rate would collapse. Error correction codes allow the vast majority of errors to be fixed on the fly, without retransmission. Behind this stand decades of mathematical research, from Reed-Solomon codes in the 1950s to modern LDPC codes and turbo codes, which bring real-world throughput within a fraction of a decibel of the theoretical limit set by Claude Shannon. And now the signal is restored. The voice sounds in the speaker. The picture appears on the screen. Data arrives in the network. The journey is complete.
an electrical signal was born in a modulator, converted to a radio wave, amplified, focused by a parabolic antenna into a narrow beam, sent across 22,000 miles of void to a satellite, received by its antenna, amplified by a transponder, sent back down to Earth, caught by another parabolic antenna, carefully amplified with minimal added noise, converted back to a lower frequency, and finally decoded, corrected, and turned back into information. The entire trip, from transmitting antenna to receiving antenna, took how long? And here we arrive at the second great conflict of satellite communication. If 200 decibels of free space loss is the first enemy, the main one, the one engineers battle every day, then the second enemy is more elusive. It cannot be defeated. It cannot be worked around. It cannot be reduced by any engineering solution. Because this enemy is the fabric of the universe itself, the speed of light. Here it is worth pausing to give one more analogy for the link budget, because it is truly the central tool of the satellite communications engineer, and I want you to feel it. Before we look at the link budget analogy, it is worth noting a cultural detail that says something about the satellite engineering profession. In terrestrial cellular communications, power is typically measured in decibel milliwatts, decibels relative to 1 milliwatt. In satellite communications, it is measured in decibel watts, decibels relative to 1 watt. The difference is 30 decibels. Minus 126 decibel watts is the same as minus 96 decibel milliwatts. The same watts, just a different reference point. Why the difference? Historical reasons. In the 1970s, when the culture of satellite engineering was forming, someone wrote an influential textbook using decibel watts, and the convention stuck. As one professor from our source materials puts it directly, it is a cultural thing. Engineering, for all its rationality, has its traditions too. And while we are on numbers and units, here is one more detail that professionals find useful. Thermal noise power in a 1 Hz bandwidth at room temperature, about 72 degrees Fahrenheit, works out to roughly minus 228 decibel watts per hertz. This is a fundamental constant. The thermal noise floor at a given temperature in a 1 Hz band. It sets the absolute lower limit on noise. You cannot go below it unless you cool the receiver to cryogenic temperatures. And every link budget begins from this number. Minus 228 decibel watts per hertz. From there, upward. Every component adds or subtracts its decibels. There is something almost meditative in this arithmetic. Numbers in the 200 to 230 range, which look terrifying to the uninitiated, are just rows in a spreadsheet for the engineer. Plus, minus, total. Does it work? It works. Next project. Imagine you are planning a road trip across a desert. You have a full tank of gas. That is your transmitter. You know your car's fuel consumption. Those are your cable losses. You know the distance to your destination. That is free space. You know there will be hills along the way, atmosphere, stretches of bad road, rain, and possible detours, additional losses. And you know that on the far side of the desert there is a gas station, but only if you arrive with at least a gallon left in the tank. A link budget is the calculation. Will you make it? Will there be enough fuel? With how much margin? Every element is either consumption or reserve. EIRP is your full tank plus your engine's efficiency.
Free space path loss is the distance of the journey. Atmospheric losses are the hills. Rain margin is the buffer in case the road turns out worse than expected. And the receiver's minimum sensitivity is that last gallon in the tank, without which you do not arrive. A satellite engineer runs this calculation before every project. They take the transmitter power in decibel watts, add the transmit antenna gain in decibels, subtract cable loss in decibels, subtract free space path loss in decibels, subtract atmospheric loss in decibels, add the receive antenna gain in decibels, subtract receive cable loss in decibels, and arrive at the signal level at the receiver input. Then they compare it to the receiver noise level and obtain the signal-to-noise ratio. If it is sufficient, the link works. If not, something must change. The antenna, the power, the frequency, the data rate.
The beauty is that in decibels, those odd logarithmic units, all of these operations reduce to simple addition and subtraction. Plus, minus, total. A person who does this professionally can estimate a basic link budget in their head in a minute. Transmitter 10 watts, 10 decibel watts. Antenna plus 50. EIRP 60. Minus 205 for free space. Minus 3 for atmosphere. Plus 52 for the receive antenna. Total minus 96 decibel watts. Minus noise floor. Enough with 6 decibels to spare. It works. Simple, elegant, powerful. 186,000 miles per second. That is the fastest anything in the universe can travel. Nothing can move faster. Not matter, not energy, not information. No technology will ever overcome this limit, because it is a law of nature so fundamental that all of modern physics is built on it as a foundation. Radio waves are electromagnetic radiation. They travel at the speed of light,
at exactly the same speed as visible light. X-rays, gamma rays, all electromagnetic waves move at the same speed in vacuum. 186,000 miles per second. A geostationary satellite hangs at an altitude of 22,000 miles. A radio signal traveling from a ground station to the satellite crosses that distance in, let us calculate, 22,000 miles divided by 186,000 miles per second equals about 119 thousandths of a second. 120 milliseconds, roughly 1/8 of a second. Not much, you might think, but that is only one way. The signal must reach the satellite and come back. 120 milliseconds up, 120 back. 240 milliseconds, nearly a quarter of a second. And that is the minimum for a station located directly beneath the satellite, on the equator.
If the station is at higher latitudes, in Europe or Canada say, the distance to the satellite is slightly greater because you are looking at it from an angle, and the delay increases to 270 or 280 milliseconds one way. And that is not all. If two people are talking through a satellite, one in London, one in New York, the signal may travel 4 legs: London to satellite, satellite to gateway station, back up to satellite, satellite to New York. This is called a double hop. In that case, the delay doubles. It can reach half a second or more. Half a second. Think about that. You say a sentence. Half a second of silence passes. Only then does your listener hear your words, and their response will reach you after another half second. The total delay from your question to their answer is about a second, plus however long they need to think. Anyone who has ever watched a live satellite link on the news a host in the studio asking a question of a correspondent on the other side of the world, knows this awkward pause. The host asks. Silence. The correspondent stands with an unmoving face. More silence. Then the answer. The viewer thinks the correspondent is slow. In reality, they are simply waiting for light to carry the host's words to them. The speed of light, 186,000 miles per second, is fast enough to seem instantaneous on Earth. But at satellite distances, it turns out to be perceptibly, annoyingly, inevitably finite. For television broadcasting, this delay does not matter. You are simply watching a picture that arrived a quarter of a second after it was filmed, and you never notice. For data transfer, downloading files, loading web pages, the delay is unpleasant but bearable. But for real-time conversation, phone calls, video calls, the delay is painful.
It breaks the natural rhythm of dialogue. People start talking over each other, mistaking the pause for the end of a sentence. The conversation becomes clumsy and exhausting. The International Telecommunication Union, ITU, has recommended that one-way delay for voice communication should not exceed 150 milliseconds. Above that, conversational quality noticeably suffers. But a geostationary satellite delivers a minimum of 240 milliseconds one way, 60% above the recommended limit. And that is the best case. Let us dwell a bit longer on what that quarter-second delay means in practice, because the consequences ripple far beyond voice calls. Consider an internet browsing session through a geostationary satellite. Every time you click a link, your request must travel 22,000 miles up, 22,000 back down to the internet backbone, and the response must travel 22,000 up and 22,000 back down to you. That is 4 legs, roughly half a second of pure propagation delay before a single byte of the web page arrives. And modern web pages are not single files. They contain dozens or hundreds of objects, images, scripts, style sheets, each requiring its own request. Conventional internet protocols like TCP were designed for terrestrial networks, where round-trip delay is a few tens of milliseconds. Over a satellite link with half a second of round-trip delay, TCP's handshaking and acknowledgement mechanisms become painfully slow. The protocol spends most of its time waiting for acknowledgements rather than sending data. Satellite internet providers have developed clever workarounds. TCP acceleration. Proxy devices that break the long satellite link into shorter segments, spoofing acknowledgements locally, so that the sender does not have to wait for the real acknowledgement from across the void. Prefetching. Predicting which objects a web page will request and sending them before the browser asks. These techniques significantly improve the user experience, making geostationary satellite internet usable for web browsing, even with the quarter-second delay. But they cannot eliminate the underlying limitation. The delay is always there. You feel it in every click, every page load, every loading spinner. For online gaming, the quarter-second is devastating. In a fast-paced game, 250 milliseconds of latency means your character responds to your command a quarter of a second after you press the button. Against opponents on fiber connections with 20 millisecond latency, you are always behind. This is one of the main reasons gamers in areas served only by geostationary satellite internet have been early and enthusiastic adopters of low-orbit services like Starlink, which bring latency down to the 20 to 40 millisecond range. For financial trading, where milliseconds matter and firms spend millions to shave microseconds off their connections, geostationary satellite delay is out of the question. But inter-satellite links through vacuum, where light travels faster than in fiber, that is interesting to traders, and the possibility of lower latency transoceanic routes through space is being actively explored. Even for applications that tolerate delay, the quarter-second has design implications. Video conferencing over satellite requires larger buffers and more aggressive echo cancellation. Remote surgery, already demonstrated over terrestrial links, becomes impractical over geostationary satellite because a surgeon needs instantaneous feedback.
File synchronization, cloud computing, real-time collaboration tools, all are affected. The ITU recommendation of 150 milliseconds one-way delay for acceptable voice quality was established decades ago, and it reflects a deep truth about human perception. We are exquisitely sensitive to delays in conversation. 100 milliseconds is barely noticeable. 200 is uncomfortable. 300 makes dialogue stilted and frustrating. Half a second makes natural conversation impossible. The geostationary satellite, for all its magnificent engineering, sits on the wrong side of this perceptual threshold for interactive communication. And that is why the low-orbit revolution, for all its cost and complexity, was inevitable. The physics of human perception demanded it. Engineers tried to fight this problem in various ways. Echo cancellation. Algorithms that recognize and remove the echo of your own voice coming back half a second later. Silence compression. The transmitter goes quiet when you are not speaking. All of this helped make satellite telephony tolerable. But it did not solve the fundamental problem. The delay was still there, a quarter of a second, the inevitable price of orbital altitude. And here, engineers asked a question that changed the entire industry. It sounded simple. What if we put the satellite lower? Think about it. Delay is proportional to distance. If the satellite is at 22,000 miles, delay is 120 milliseconds one way. What if the satellite is at 600 miles? 600 divided by 186,000. That is 3.5 milliseconds. One way. 7 milliseconds round trip, practically unnoticeable, comparable to an ordinary ground-based fiber optic connection. Sounds like an obvious solution. Lower the satellite, reduce the delay. Problem solved. But it is not that simple. And behind that, not that simple, hides one of the most ambitious, most expensive, and most dramatic engineering gambles in the history of telecommunications. Recall why geostationary orbit is so convenient. The satellite hangs motionless. One ground antenna, pointed at one spot in the sky, maintains communication around the clock. 3 satellites cover the entire Earth. The architecture is simple, predictable, elegant. Now imagine you lower the satellite to 600 miles. What happens? First, it stops being motionless. At that altitude, the orbital period is not 24 hours, but roughly 100 minutes. The satellite races across the sky at about 15,500 miles per hour. It sweeps from horizon to horizon in minutes. Then it vanishes. This means a ground antenna pointed at that satellite will have a connection for only a few minutes per pass. Then the satellite flies away, and the antenna must switch to the next satellite appearing over the horizon. For this to work, there must always be at least one satellite in the sky, preferably several, to ensure continuity and seamless handoffs. How many satellites does that require? This is where the math begins. In geostationary orbit, each satellite sees roughly a third of the Earth's surface. 3, and the whole planet is covered. But in low orbit, each satellite sees only a small circle of surface directly below it. Its coverage footprint is much smaller.
The lower the orbit, the smaller the circle, the more satellites you need to tile the entire surface. And since the satellites are moving, the circles are moving too, and you need satellites in multiple orbital planes, tilted at different angles, to keep the coverage even and continuous. The calculation shows the order of magnitude. For global coverage from low orbit, you need dozens, more often hundreds, of satellites.
Not 3, not 10, hundreds.
And if you want gap-free coverage with guaranteed continuity and enough capacity for a large number of users, the count goes into the thousands. This is a radically different economics. A geostationary satellite is expensive, hundreds of millions of dollars. But one satellite serves an entire region. A low-orbit satellite may be cheaper per unit, but you need 100 or 1,000 times more. Plus, each one lives shorter. At low altitude, residual atmospheric drag slowly decelerates the satellite and lowers its orbit until it burns up in the atmosphere after 5 to 7 years. A geostationary satellite serves 15 to 20. A low-orbit one, half that, or a third, and it must be continuously replaced. And one more problem, less obvious but critical: handover. The ground terminal must continuously track a moving satellite, and when it disappears over the horizon, instantly switch to the next one without dropping the connection.
This requires antennas that can change direction quickly, or electronically steered phased array antennas that can switch their beam almost instantly, with no physical movement. Such antennas exist, but they are significantly more complex and expensive than a simple fixed dish. There is one more challenge of low-orbit satellites that we should mention: the sheer logistics of constellation management. A geostationary satellite sits in one spot. You launch it, park it, and forget about its position for 15 years. Save for small periodic corrections. A low-orbit constellation of thousands of satellites is a living, breathing organism. Satellites are continuously launched to replace those that deorbit. Their orbits must be actively managed, raised, lowered, adjusted to maintain proper spacing. Collision avoidance maneuvers must be performed whenever tracking data shows two objects approaching dangerously close. And each satellite has a limited lifespan,
5 to 7 years before atmospheric drag pulls it down. This means the operator is never done launching. A constellation of 4,000 satellites, each lasting 5 years, requires about 800 replacement launches per year just to maintain the constellation at full strength. Roughly 2 launches per day if each rocket carries 60 satellites. This is an industrial operation of a scale never before attempted in space. It is more like running an airline, with its continuous cycle of flights, maintenance, and fleet replacement, than like traditional satellite operations, where you launch a satellite and operate it for 2 decades. The operational complexity is immense.
Ground control systems must track thousands of satellites, manage their orbits, schedule their communications windows with ground stations, handle handovers between satellites and users, manage interference between beams, coordinate with other constellation operators and with space surveillance networks to avoid collisions. All of this runs on software, sophisticated, constantly updated, never sleeping. The satellite is simple. The system that manages thousands of satellites is extraordinarily complex. The first company to attempt all this, to build a global low-orbit satellite network for voice communication, was Iridium. And the story of Iridium is one of the most gripping and tragic business stories in telecommunications history. The project was born inside Motorola in the late 1980s. Legend has it that the idea came to engineer Barry Bertiger when his wife complained that she could not make a phone call from their Caribbean vacation. The concept was ambitious. 66 satellites in low orbit at about 485 miles altitude, distributed across 6 orbital planes. A system that would let you call from any point on the planet to any other directly through the satellite, without ground infrastructure. The satellites were linked to each other by radio crosslinks. A signal could hop from satellite to satellite, traveling across the orbital network until it reached a satellite visible from the destination. A global network in the sky. Originally, the project called for 77 satellites, matching the number of electrons in an atom of iridium, element 77 in the periodic table, hence the name. When the number was reduced to 66, someone joked that the system should be renamed dysprosium, element 66. The joke did not stick. The system cost roughly $5 billion. All 66 satellites were successfully placed in orbit. On November 1st, 1998, the Iridium network began commercial service. And almost immediately, it became clear that something had gone catastrophically wrong. Not with the technology worked. With the market. While Iridium was being developed, a process that took over 10 years, the world around it changed. In the late 80s, when the project was conceived, mobile phone service was expensive, rare, and covered mainly large cities. The idea of a satellite phone that works everywhere seemed revolutionary. But by the time of launch, in '98, terrestrial cellular networks had spread everywhere. GSM covered most populated areas. The mobile phone had gone from luxury to commodity. And it turned out that the number of people who truly need a phone that works deep in the wilderness, in the middle of the ocean, or in the heart of the Sahara, and who are willing to pay $3 to $6 a minute and carry a brick-sized handset, was far smaller than the business plans assumed. On August 13, 1999, 9 months after launch, Iridium LLC filed for bankruptcy. It was one of the largest corporate bankruptcies in American history. Destroying the entire constellation was seriously discussed, deorbiting all 66 satellites and burning them in the atmosphere. A $5 billion system into the fire. But that did not happen. A group of investors purchased the entire system for $25 million, 1/200th of the cost of building it. Under new management, with radically reduced pricing and a focus on niche markets, maritime, aviation, military, expeditions, journalists in conflict zones, Iridium slowly, painfully, but steadily became profitable. Today, Iridium is a successful company with a second-generation constellation, Iridium Next, and contracts generating hundreds of millions of dollars annually. The technology won. The business model, after death and resurrection, won too. Let us expand the Iridium story a little more, because it contains details that beautifully illustrate how thin the line is between technical triumph and commercial catastrophe. The Iridium engineering team at Motorola designed a system of unprecedented complexity. 66 satellites at about 485 miles, distributed across 6 orbital planes, inclined at 86.5 degrees to the equator, nearly polar orbits, to cover the polar regions too. Each satellite weighed about 1,500 pounds and carried 48 beams, each serving its own cell on the ground. Exactly like the cells in a terrestrial cellular network, except the cells moved with the satellite. When one satellite passed out of view, active calls were handed over to the next satellite without interruption. Technically, the system was magnificent. It worked. But the market it entered in 1998 looked nothing like the market it was designed for in '87.
Over those 11 years, the mobile revolution had happened. Cellular networks covered most populated areas, and it turned out that the overwhelming majority of people, even frequent travelers, did not need a phone that works in the middle of the Sahara. They needed a phone that works at the airport, at the hotel, and on the city street. The Iridium handset cost about $3,000. A call ran $3 to $6 a minute. The phone was the size of a brick, worked only outdoors. The signal could not penetrate roofs or walls, and voice quality was noticeably worse than terrestrial cellular. For the mass market, unacceptable. For niche users, mariners, oil rig workers, polar researchers, military personnel, the product was excellent. But there were too few of them to recoup a $5 billion investment. The new owners, who bought the system for $25 million, refocused on exactly those niche markets. The US Department of Defense became one of the largest customers. Maritime and aviation operators signed long-term contracts. Emergency services, scientific expeditions, journalists in remote locations, all found Iridium indispensable. Without the burden of $5 billion in debt, and with the right market focus, the business began to grow. By the 2020s, Iridium had launched an entirely new constellation. 66 second-generation satellites, Iridium Next, and reached sustained profitability with annual revenue exceeding $700 million. The lesson: even flawless technology can fail if it meets the wrong market or arrives at the wrong time. Another project of the same era, Teledesic, backed by Bill Gates, envisioning 840 satellites for global broadband, was cancelled without launching a single working spacecraft. Technology kept outrunning the market, or the market kept changing faster than the technology could arrive. This is why the success of Starlink, if it holds over the long term, is all the more remarkable. SpaceX learned from every predecessor's mistake. Vertical integration, own rockets, own satellite factory, own terminals, allowed cost control at every stage. Rapid iterative deployment, rather than all or nothing, allowed revenue to start flowing before the full constellation was complete. And crucially, the market had finally matured. Broadband internet had become a basic necessity, and millions of people in rural and remote areas desperately needed connectivity that ground networks could not provide. The alignment of technology, economics, and demand, that is what makes satellite communication commercially viable. Physics says it can be done. Engineering shows how. But only the market decides whether it is worth doing. And then came Starlink. In 2015, Elon Musk, founder of SpaceX, announced a project whose scale made many in the satellite industry assume he was joking. The project was called Starlink. The idea: launch not 66 satellites into low orbit like Iridium, but thousands. The initial filing with the Federal Communications Commission called for about 12,000 satellites. Later the number grew to 30,000, then 42,000. For comparison, in the entire history of spaceflight, from 1957 through 2020, humanity launched about 11,000 satellites total. Musk was proposing to put up 4 times that number. Many thought it impossible. But Musk had an advantage the Iridium builders lacked: his own rocket company. SpaceX had radically reduced launch costs by learning to recover and reuse Falcon 9 first stages, and SpaceX could launch at speeds previously unimaginable. 60 satellites per launch, launches every few weeks, and at times every few days. By 2026, thousands of Starlink satellites are in orbit, providing broadband internet across much of the Earth's surface,
including remote areas where cable or fiber never reached. Latency: 20 to 40 milliseconds, nearly on par with terrestrial systems. That quarter second that tormented geostationary users has essentially vanished.
The user terminal is a small flat antenna, roughly a foot across, with electronically steered beam. A phased array antenna. No motors, no physical rotation. The antenna switches beam direction electronically in milliseconds, tracking a moving satellite and switching to the next when the current one moves out of range. From the user's perspective, it is simply a dish you put on your roof, plug into a router, and get internet. All the complexity, thousands of satellites, orbital mechanics, Doppler shift from satellite motion, handover between satellites, is hidden inside. The Starlink user terminal deserves a few more words because it represents a genuinely remarkable piece of consumer electronics engineering. The terminal is roughly 12 inches across and about an inch thick. It contains no motors and no moving parts of any kind. Inside, there are hundreds of tiny antenna elements arranged in a flat grid, each with its own amplifier and phase-shifting circuit. By electronically adjusting the phase of each element, the terminal steers its beam to track a satellite crossing the sky, then switches to the next one as it approaches, without any physical motion. The transition happens in milliseconds, fast enough that the user's internet connection is uninterrupted. The terminal also compensates for the Doppler shift caused by the satellite's motion. A Starlink satellite at 340 miles altitude moves at roughly 17,000 miles per hour relative to the ground. This motion shifts the received signal frequency by several tens of kilohertz. The terminal's receiver must track and correct for this shift continuously, or the demodulation fails. All of this, beam steering, Doppler tracking, handover management, power control, happens automatically, transparently, inside a device that the user simply plugs in and forgets about. Early versions of the terminal cost SpaceX more to manufacture than the price they charged customers. A common pattern in technology businesses, where the hardware is subsidized and profits come from service subscriptions. As manufacturing scaled and costs dropped, the economics improved. The terminal is now one of the most sophisticated pieces of consumer radio equipment ever mass-produced. A phased array antenna that a decade ago would have been found only in military installations, now sitting quietly on a suburban rooftop, pulling internet from space. And that, perhaps, is the most telling measure of how far satellite communication has come. From Sputnik's 183-pound sphere beeping at 20 megahertz to a 12-inch flat panel silently tracking thousands of satellites and delivering hundreds of megabits per second to a home Wi-Fi router. From a Christmas greeting broadcast from orbit in 1958, barely audible through the static, to 4K video streaming from a satellite constellation in real time. From Arthur Clarke's 4-page article in Wireless World, politely ignored, to a global industry generating hundreds of billions of dollars a year. 70 years. Less than one human lifetime. From an idea on paper to an invisible infrastructure that holds the world together. But geostationary satellites have not gone away. They have their own unassailable advantages. One geostationary satellite covers a third of the Earth's surface. It is stationary, which radically simplifies ground antennas. It requires no handover. For television broadcasting, where delay does not matter, and you need to simultaneously send the same signal to millions of receivers, the geostationary satellite
remains unmatched. One broadcast, 1,000,000 dishes, each costing a few dozen dollars, permanently aimed at one point in the sky.
Try replicating that with a constellation of thousands of moving satellites. The two worlds, geostationary and low orbit, do not replace each other. They complement each other. Geostationary for broadcasting, for stable, fixed-point links, for covering whole continents with one spacecraft. Low orbit for interactive internet, for low-latency communication, for mobile users who need fast response. Satellite communication of the future is not one answer, but a spectrum of solutions, each filling its own niche. And between these two tiers sits a third, medium Earth orbit, or MEO. Satellites at about 5,000 miles altitude, where the round-trip delay is roughly 54 milliseconds, far better than geostationary, and needing far fewer satellites than low orbit.
The O3b system, standing for Other 3 Billion, named for the 3 billion people who lacked internet access, flies at about 5,000 miles and delivers broadband with noticeably lower latency than geostationary. Navigation satellites like GPS and Galileo also orbit at medium altitude, around 12,400 miles. 3 tiers of satellite communication: LEO, MEO, GEO. Each an answer to the same question asked in a different context. How much delay can we afford? Meanwhile, thousands of satellites in low orbit raise new concerns: orbital debris and the risk of collision. Light pollution. Sunlight reflected off satellites interferes with astronomical observations. Frequency coordination. Thousands of new transmitters create potential interference with existing systems. The Kessler syndrome, described by NASA researcher Donald Kessler in 1978, warns of a cascading chain reaction. One collision produces debris. That debris causes more collisions, which produce more debris, until an entire altitude range becomes unusable. Low-orbit satellites are designed with limited lifespans. They naturally deorbit and burn up in the atmosphere within 5 to 7 years, a built-in self-cleaning mechanism. But the risk grows as the number of objects in orbit grows, and global coordination protocols are still being developed. Imagine that above the equator, at 22,000 miles up, there runs an invisible ring, thinner than a cobweb, about 165,000 miles long. And this ring is the most valuable piece of real estate in the solar system, because it is the only line in space where a satellite can remain motionless relative to the Earth. The geostationary orbit, Clarke's orbit, and it is finite.
Satellites on this orbit cannot stand shoulder to shoulder. They must be separated by at least 2 to 3 degrees of longitude so that ground antennas can distinguish one from another and not aim at the wrong satellite. 2 degrees translates to roughly 900 miles at geostationary altitude. Across the entire visible arc, there are roughly 180 parking spots, orbital positions, each defined by its longitude, each as prized as a plot of land in Manhattan. Who assigns these positions? The International Telecommunication Union, ITU. This organization, established in 1865 and one of the oldest international bodies in existence, coordinates the global use of radio frequencies and orbital positions. The ITU divides the world into 3 regions: Region 1, Europe, Africa, Russia; Region 2, the Americas; Region 3, Asia and Australia. For each region, there are rules governing frequency use and orbital slots.
But the orbital position is only half the equation. The other half is frequency spectrum. Each satellite operates in a specific frequency band,
and the amount of available spectrum is limited by physics and international agreements. In each band, C, Ku, Ka, there is a fixed set of frequencies allocated for satellite communication, and those allocations are not infinite. How do engineers squeeze more capacity out of limited spectrum? One of the most elegant methods is frequency reuse through polarization. An electromagnetic wave oscillates in a specific direction. It's polarization. Two waves at the same frequency, but with different polarizations, do not interfere with each other. An antenna tuned to horizontal polarization barely picks up a vertically polarized signal, and vice versa. This means you can use the same frequency band twice, once with horizontal polarization and once with vertical, or once with right-hand circular and once with left-hand circular. Capacity doubles without allocating any new spectrum. Another method is spatial reuse. A satellite can form multiple narrow beams aimed at different parts of the Earth's surface. Different beams can use the same frequencies because they are spatially separated. The signal from one beam does not reach the zone of another. Like separate rooms in a building, each playing the same radio station, but the walls block the sound and there is no interference. Modern high-throughput satellites, HTS, use dozens or hundreds of such beams, reusing the same spectrum many times over and achieving total capacity of hundreds of gigabits per second from a single spacecraft. The electromagnetic spectrum deserves one more thought, because there is something profound about it if you step back. The spectrum is a shared inheritance of all humanity. It belongs to no country, no company, no individual. It belongs to physics. And the task of the international community, through the ITU and national regulators, is to manage it so that everyone, satellite operators, mobile networks, broadcasters, scientists, military, can work without interfering with each other. The ITU holds World Radio Communication Conferences every few years, where representatives from nearly every nation negotiate the allocation of frequencies among hundreds of different services, from AM radio to radars, from cellular to radio astronomy. Every decision is a trade-off. Every new band given to one service is taken from another. Every country has its own priorities, and the negotiations can be fierce because spectrum translates directly to revenue. A slice of bandwidth in a favorable band can be worth billions of dollars. In this arena, orbital positions and frequency allocations are often compared to real estate. A geostationary orbital slot at a desirable longitude, paired with a favorable frequency allocation, is like a prime piece of commercial property. It generates revenue for decades. It can be leased, traded, fought over in regulatory proceedings. Entire companies, like the Luxembourg-based SES, one of the world's largest satellite operators, are built around portfolios of orbital slots and spectrum rights, much as real estate companies are built around portfolios of land and buildings. The difference, of course, is that you cannot build more spectrum. The electromagnetic spectrum is fixed by physics. You can use it more efficiently, through better modulation, through spatial reuse, through dynamic allocation. But you cannot create more of it. This is the fundamental scarcity that drives the entire economics of satellite communication, and of telecommunications more broadly. And it is why the battle for spectrum will only intensify as demand grows and supply remains constant. And here we should mention a conflict unfolding right now. As terrestrial 5G networks expand, the frequencies they want to use, around 3.5 GHz, sit right next to the C-band that satellites have used for decades. Powerful ground-based 5G transmitters can create interference for satellite receivers
accustomed to a quiet radio environment. The solution involves special filters, migration of satellite services to other frequencies, and guard bands between the two systems. The battle for spectrum, for this invisible resource, continues. Now let us talk about antenna types at a broader level, because we have been discussing parabolic dishes and phased arrays, and the difference between these two approaches is worth understanding clearly. A parabolic antenna is a mechanical device, one large reflective surface, one feed horn. To point the beam at a different satellite, you must physically turn the entire antenna, by motors or by hand. This is simple, reliable, and cheap. Parabolic antennas are manufactured by the millions, from small home dishes costing $30 to enormous 60-foot structures standing on concrete foundations. Their main limitation: they can only look in one direction at a time, and switching direction requires physical movement. A phased array antenna takes a completely different approach. Instead of one large reflector, it uses an array of hundreds or thousands of small radiating elements arranged on a flat surface. Each element receives its own signal, slightly shifted in phase relative to its neighbors. By controlling the phase shifts, doing it electronically with no moving parts, the combined beam can be steered in any direction. Switching direction takes microseconds. No motors, no bearings, no wear. Sounds ideal, but phased arrays are significantly more expensive than parabolic antennas of comparable gain. Each of the hundreds of elements has its own amplifier and phase shifter.
The electronics are complex and power-hungry. Until recently, phased arrays were used almost exclusively in military radars and air defense systems, where cost is not a constraint, but beam switching speed is critical. What changed? Mass production. When SpaceX began manufacturing Starlink user terminals by the hundreds of thousands, the cost of a phased array per terminal dropped from tens of thousands of dollars to a few hundred. The same logic that made smartphones cheap, economies of scale and automated manufacturing, began working for antennas. This is one of the reasons low-orbit constellations became economically viable now and not 20 years ago. Between the two types, there are also hybrid solutions. Antennas with mechanical steering for coarse pointing and electronic fine-tuning. Parabolic antennas with multiple feed horns, each looking in a slightly different direction, allowing coverage of several satellites without rotating the dish. Engineering never stands still.
Let us also appreciate the scale of what happens every day, above and around us. Right now, more than 500 active communications satellites are in geostationary orbit. Each serves a specific region: Europe, Asia, Africa, the Americas, the Pacific. Each carries dozens of transponders. Each transponder handles a band of 36 or 72 megahertz. The combined throughput of all geostationary communications satellites is hundreds of terabits per second. And alongside them, thousands of low-orbit constellation satellites add tens and hundreds more terabits. All of it invisible. All of it silent. Signals passing through your body, through the walls of your home, through clouds and atmosphere. And you do not notice them, unless you have a receiving antenna and a demodulator. Radio waves are part of the electromagnetic spectrum that our senses cannot perceive. We see light, a narrow band from violet to red. We feel infrared as heat, but microwaves, the gigahertz range, are completely invisible, inaudible, intangible. And yet, they carry a substantial share of all the information humanity exchanges. Think about that. Above your head, right now, in total silence, trillions of bits of information are flying. Television channels
Someone is watching on the far side of the country. Phone conversations between people on different continents. Data from weather satellites that are forming tomorrow's forecast right now. Navigation signals your phone uses to show your position on a map within a few feet. Distress signals from ships in the ocean. Military communications. Banking transactions. Scientific data from orbiting observatories. All of this information follows the same path we traced tonight. Modulator, cable, BUC, antenna, atmosphere, 22,000 miles of void, satellite, back down, antenna, LNB, cable, demodulator. Every time, 100-fold billion loss.
Every time, a battle for every decibel. Every time, a victory of engineering over distance. There is one more law that stands behind everything we have discussed. It is not about orbits or antennas. It is about information. And it sets an absolute ceiling on how much data can be transmitted through any communication channel. Satellite, cable, fiber, any. In 1948, 17 years before the first geostationary communications satellite, 9 years before the first Sputnik, an American mathematician and engineer named Claude Shannon published a paper that laid the foundations for all of modern information theory. Shannon worked at Bell Labs, the legendary research laboratory of AT&T, and his paper was titled A Mathematical Theory of Communication. It changed the world no less than the transistor or the atomic bomb, though its influence was quieter. Among the many results in that paper is one formula that directly concerns our topic,
The channel capacity formula. It says this: the maximum rate at which information can be transmitted through a communication channel without errors is determined by two things: the bandwidth of the channel and the ratio of signal power to noise power. And that is it. Nothing else. No matter how much you improve the modulation, the coding, the antennas, you cannot push more data through the channel than Shannon's formula allows. It is a theoretical ceiling, like the speed of light for travel, absolute and insurmountable. And here is what is striking. Over recent decades, thanks to advances in digital signal processing, coding, and modulation, engineers have approached Shannon's limit very closely. Modern satellite communication systems operate within a few tenths of a decibel of the theoretical maximum. Squeezing even a bit more out of the same spectrum through smarter coding is now essentially impossible. The ceiling has been reached.
What this means for the future is that increasing satellite communication capacity now depends not on cleverer modulation, but on two other things: more spectrum, higher frequencies, Ka band and above, and spectrum reuse, spatial separation, multi-beam antennas, new orbits. The engineering battle has moved from the signal level to the architectural level. Not how to shout louder, but how to arrange many quiet conversations so they do not interfere with each other. There is something beautiful in that, if you think about it. Half a century ago, the main challenge was to reach the satellite at all, to overcome 200 decibels. Today, that challenge is solved. The main challenge now is not to shout, but to speak quietly, but in many channels at once, simultaneously, efficiently, using every hertz of spectrum, every degree of orbital arc, every watt of satellite power, with maximum efficiency.
The frontier has shifted from raw physics to architecture, coordination, and mathematics. A few more words about the regulatory side, because a satellite hanging over the equator broadcasts its signal not to one country, but to an entire continent. A radio wave does not know national borders. A satellite beam aimed at Central Europe inevitably covers the territories of dozens of countries. Physically restricting the signal to one nation is impossible. The beam shape is determined by the satellite's antenna, and it covers the entire region. This creates an interesting regulatory situation. A satellite operator works in a specific frequency band, coordinated through the ITU. But providing services, television, internet, telephony, in each specific country requires a separate license from the national regulator. The operator may have the right to broadcast at 14 GHz over Europe, but to legally sell satellite internet in France, they need French authorization.
In France, one set of rules, in Germany another, in Poland a third. There are sharper situations too. Some countries do not want their citizens receiving certain satellite channels for political or ideological reasons. Physically preventing it is impossible. Anyone with a dish of the right size and a decoder can catch the signal. The only options are encryption, so only subscribers with an authorized decoder can watch, or legal prosecution of those who receive unauthorized content. A satellite is, by definition, transboundary. It cannot tell a viewer in one country from a viewer in another. The radio wave does not care. This transboundary nature is simultaneously a strength and a vulnerability. A strength because one satellite can serve an entire continent without building infrastructure in each country. A vulnerability because regulatory barriers in each country create a patchwork of rules the operator must navigate. And a note on the future.
We mentioned that satellites currently use frequencies up to Ka band, about 40 GHz. But research and experiments push higher. Q band, 33 to 50 GHz, and V band, 40 to 75 GHz, are being considered for future systems. Higher still, optical communication, transmitting data by laser at the frequencies of visible or near-infrared light. Optical inter-satellite communication is already in use, and optical links from satellite to ground have been demonstrated in clear weather, delivering throughput impossible for radio frequency systems. Perhaps in 20 or 30 years, satellites will send data to Earth not by microwaves, but by laser light, invisible but carrying hundreds of gigabits per second. Whatever the technology of the future, radio waves, lasers, something else entirely, the fundamental principles we discussed tonight will remain. The inverse square law will not go away. The speed of light will not increase.
Noise will not vanish. The atmosphere will not become transparent. Orbital mechanics will not change. Everything that satellite communication engineers have learned over the past half-century, all of this system of trade-offs, balances, and carefully calibrated decisions will remain relevant for as long as humans send signals through space. And if there is one thing to take away from this entire story, one thought that unites all the frequencies, all the orbits, all the antennas, and all the formulas, it is this. Satellite communication is the story of how people learned to make the impossible possible. Not once, but again and again, at every stage. Send a signal across 22,000 miles of void. Impossible? Possible, with a parabolic antenna and an amplifier. Receive a signal carrying trillionths of a watt. Impossible? Possible, if the amplifier is quiet enough. Maintain a link to a moving satellite. Impossible?
Possible, if the antenna can switch its beam in milliseconds.
Cover the entire Earth from low orbit. Impossible? Possible, if you launch thousands of satellites. Every time physics raised a barrier, engineers found a way around it, not by breaking the laws of physics, that is impossible, but by using other laws of physics as compensation. The inverse square law takes 200 decibels. The geometry of the parabola returns 50. Thermal noise masks the signal. Low noise amplifiers bring the noise down to tens of kelvins. The speed of light creates delay. Lower the orbit and launch thousands of satellites. Spectrum is finite. Reuse it through polarization and spatial separation. Every answer breeds new questions. Every solution creates new problems. And engineers keep working, quietly, stubbornly, invisibly, like the satellites they launch. Let us stop and look back at the entire path we have traveled together.
We started with a modulator in a ground station, an electrical signal running through a cable. We saw how the Book C shifts it to the working frequency and amplifies it. How a parabolic antenna, using geometry known to the ancient Greeks, gathers that power into a narrow beam, boosting it 100,000 times. How that beam pushes through the atmosphere, through rain, water vapor, clouds, losing a few decibels or a dozen in the heaviest downpour. And how the signal then exits into space, into the void, where nothing acts on it except the inverse square law, relentlessly smearing its energy across the surface of an expanding sphere. 200 decibels, 100 billion times. From a watt to a billionth of a watt. We saw how this ghostly signal arrives at the satellite, a machine that cannot be repaired, that lives in vacuum for 15 years, powered by solar panels, rationing every watt.
How the satellite's transponder receives this whisper, amplifies it, shifts its frequency, and sends it back down. And how, on the ground, another parabolic antenna catches this twice-weakened whisper, and the low-noise converter, the LNB, amplifies it with surgical care, adding the barest minimum of its own noise. And how, finally, the demodulator and error correction codes reconstruct the original information, voice, picture, data, with virtually no loss. And we saw the second great conflict, the conflict with the speed of light. 1/4 of a second for geostationary orbit, 1/2 a second for a double hop. A delay that cannot be beaten because you cannot make light travel faster.
And the solution? Low orbit, but at the cost of immense complexity. Not 3 satellites, but thousands. Not stationary, but racing at 15,000 miles per hour. Not 15 years of life, but 5 to 7, with constant handover, electronically steered antennas, and the need to continuously replace satellites burning up in the atmosphere. The story of Iridium, as a warning that the right technology at the wrong time can cost billions. And the story of Starlink, as proof that the same technology at the right time, with the right launch economics, can change the world. And behind all of it, the fight for an invisible resource. Frequencies, orbital positions, every hertz and every degree. And Shannon's formula, standing quietly in the corner, reminding engineers that information, like light, has its own fundamental limit. Every answer breeds new questions. Every solution creates new problems. And engineers keep working, quietly, stubbornly, invisibly, like the satellites they launch. Now, before we close, let me say something about why all of this matters beyond the engineering. When a fisherman in the Pacific Ocean, thousands of miles from the nearest shore, calls home on a satellite phone, he is using everything we discussed tonight. Parabolic antenna, BUC, transponder, LNB, error correction codes, 200 decibels of loss, and their defeat. He does not think about any of that. He just hears his wife's voice. And that is perhaps the highest compliment an engineer can receive, when their work is so good that it becomes invisible. When a surgeon in a field hospital in a conflict zone conducts a video consultation with a colleague at a university clinic, 22,000 miles of vacuum and a quarter-second delay and all the engineering we discussed lie between them. The surgeon does not think about it. They think about the patient. The technology vanishes, becomes transparent. Only the connection remains, human to human. When the only communication link after an earthquake, a hurricane, or a flood is a portable satellite terminal that rescuers unpack from a suitcase, a small dish, a BUC, an LNB, a modem, 20 minutes to set up. That is satellite communication at its most essential. The satellite is up there, 22,000 miles above the disaster, unshaken, unflooded, unburned. It just works. As it did yesterday, as it will tomorrow. Satellite communication does not attract attention the way smartphones or social media do. It has no glossy interface, no viral marketing campaigns, no logo on every corner. But it literally keeps the world connected. Without it, aviation does not work over oceans. Maritime transport loses communication and navigation on the open sea. Weather forecasting loses its eyes in space. Television goes dark in half the world. Internet never reaches villages and settlements that fiber will never reach.
This is infrastructure. Invisible. Quiet. Working around the clock. Like the water supply. Like the power grid. Like the air. You notice it only when it disappears. And the engineer's job is to make sure it never does. Let us talk about a few more practical applications that most people take for granted without realizing satellite communication is behind them. Banking. When you insert your card in an ATM in a small town and get cash within seconds, it is entirely possible that your transaction's authorization traveled through a satellite. Especially if the ATM is in a location without reliable terrestrial connectivity. The satellite channel may be the backup or the primary link. Either way, you will never know. Precise timing. All modern financial systems, power grids, and telecommunications networks depend on precise time synchronization. GPS satellites and other navigation constellations transmit timing signals synchronized with onboard atomic clocks.
These signals are used not just for navigation, but for synchronizing bank systems, power stations, cellular networks. If GPS signals disappeared, the consequences would be felt far beyond navigation. Agriculture. Modern precision farming systems use satellite navigation to guide tractors to within an inch. A combine, guided by GPS signal, traverses a field with accuracy no human driver could match. Satellite imagery shows the farmer the condition of crops, soil moisture levels, pest presence, all in near real time, processed on the ground and delivered back to the farmer through a satellite link. Maritime safety. Every commercial vessel is required to carry an automatic identification system, AIS, that transmits the ship's position, course, speed, and other data via satellite. This information is collected by satellites and relayed to vessel traffic management centers, enabling the tracking of tens of thousands of ships across the world's oceans simultaneously. Emergency beacons, EPIRBs, also transmit distress signals through satellite, enabling rescue services to locate a ship in distress anywhere on the ocean within minutes. All of these applications, from ATMs to ocean rescues, depend on the same system we described. Modulator, antenna, 22,000 miles of void, 200 decibels of loss. Transponder, return path, LNB, demodulator. Every time, the same journey. Every time, the same battle with physics. Every time, the same quiet victory.
And there is one application that deserves special emphasis: communication during natural disasters. We have touched on this, but it bears repeating. When Hurricane Maria in 2017 destroyed nearly all communications infrastructure in Puerto Rico, cell towers toppled, power gone for weeks, the only working link was satellite terminals brought by rescuers.
Floods in South Asia, wildfires in California and Australia, earthquakes in Turkey and Syria. Every time, satellite communication turns out to be the only channel functioning in the first, most critical hours. Organizations like Télécoms Sans Frontières, Telecoms Without Borders, specialize in deploying satellite communication in disaster zones. They arrive with suitcases containing the same small dish, BUC-LNB modem. Within 20 minutes, the affected population has a link to the outside world. Because the satellite is up there, 22,000 miles above the earthquake, unshaken, unflooded, unburned. It simply works. The way it worked yesterday, the way it will work tomorrow. This is, perhaps, the most noble application of the technology we have discussed. When everything collapses, when the ground shakes, the water rises, the wind tears everything apart, the satellite above continues working, still, undisturbed, ready to receive a signal and send it back.
Because it was designed precisely for this. To work when nothing else does. Right now, as you lie here listening to these words, above your head, 22,000 miles up, in total darkness and absolute vacuum, hundreds of satellites are hanging motionless. Their solar panels face the sun. Their antennas face the earth. Inside each one, transponders are receiving signals, amplifying them, and sending them back, continuously, around the clock, year after year. They do not tire. They do not sleep. They simply work. Quietly, patiently, invisibly. And lower, at 300 miles up, thousands of other satellites are racing along their orbits at nearly 17,000 miles per hour. One full loop around the Earth every 90 minutes. They glint in the rays of sunset, if you know where to look. A thin chain of bright dots slowly crawling across the night sky.
Each dot is a small radio station whose antenna continuously switches between thousands of users on the ground, sending them data and receiving their requests. Tens of megabits per second for each one. No wires, no cables, no towers. Just radio waves, flying from space. Between these two worlds, geostationary and low orbit, lies all the engineering we talked about tonight. Parabolic antennas gathering the invisible. Amplifiers squeezing every decibel. Low-noise converters hearing a whisper against the thermal hum of the universe. Error correction codes rebuilding information from chaos. And people. Engineers sitting at screens, watching telemetry, calculating link budgets, planning orbit corrections, and worrying. Because worrying is their profession. To foresee what could break and to keep it from breaking. The signal you receive on your satellite receiver has traveled roughly 44,000 miles. It lost power by a factor of 100 billion, twice.
It passed through rain, through the ionosphere, through cosmic void. It was amplified by a transponder that has been working in vacuum without maintenance for a decade. It was caught by an antenna whose shape was mathematically described before the Common Era, and it was reconstructed using codes built on a theorem that Claude Shannon formulated in 1948. All of this happens every second, invisibly, silently, reliably. And perhaps that is the most comforting thought to fall asleep to. That somewhere above you, right now, in the silence of space,
An invisible network is at work. Satellites, antennas, radio waves, quietly, patiently, ceaselessly doing what it was built to do. Connecting people on opposite ends of the earth, carrying voices and pictures across the void. Conquering distance, 22,000 miles of distance, every quarter of a second. And the people who built all of this thought about things you might never have noticed. The shape of a parabola.
The noise temperature of an amplifier. The fact that rain absorbs microwaves. The fact that the speed of light, for all its unfathomable swiftness, is still finite. They thought about all of that, so that you would not have to. Let that thought be your last one as you drift off. The quiet hum of invisible radio waves above your head, satellites working in the dark, and a long, astonishing story about how people learned to send a whisper through space and hear the answer. Let it be soft and quiet, like the distant hum of something working for you while you rest. Good night.